Hello there, and welcome to Physics with William, where curiosity gets cozy, the universe takes off its shoes at the door, and science settles down beside us like an old friend with a very large telescope and a warm cup of tea. Tonight, our quiet journey takes us into one of the deepest mysteries in all of physics, a mystery so large that it fills the universe, and yet so difficult to see that we had to give it a name before we truly understood what it was. Dark energy. It sounds a little dramatic, does it not? Dark energy. Like something you might find in a suspicious bottle at the back of a wizard's cupboard, or perhaps the reason your phone battery vanishes faster when you are already late. But in physics, the word dark does not mean evil or spooky. It means unknown, unseen, not yet explained. It is the label we give to something that seems to be shaping the fate of everything while refusing to introduce itself properly. And that is rather rude of it, really. Because according to our best observations, the universe is not merely expanding. It is expanding faster and faster as time goes on. Galaxies are drifting away from one another. Space itself is stretching. The great cosmic distances are growing. And instead of gravity gradually slowing this expansion down, as many scientists once expected, something appears to be helping the universe speed up. Not stars, not planets, not black holes, not the glowing gas between galaxies. Something smoother, stranger, and spread across the cosmos like an invisible pressure in the fabric of space. That something is what physicists call dark energy. Now, before we wander too far into the dark, I would love to know something simple and human. Where are you listening from tonight? Are you tucked away in a quiet room, with the lights low and the day finally softening around the edges? Are you somewhere warm, where the night air is still, or somewhere cold, where the window glass has that faint, sleepy chill? And when you look outside, if you can see the sky at all, does it feel close and familiar, or huge and unreachable? It is a funny thing looking up at the night sky. We see stars, a few planets if we're lucky, perhaps the pale wash of the Milky Way if we're far from city lights. But what we're really seeing is only the bright embroidery on a much larger cloth. Most of the universe is not shining at us. Most of it does not announce itself with sparkle or flame. It simply leaves clues. A galaxy moving too quickly, a beam of light bent along the way, a pattern in the oldest glow of the cosmos, a distant stellar explosion dimmer than it ought to be. A vast expansion that should have been slowing down, but instead seems to have found a second wind. If you find this sort of cosmic wandering soothing, or if you enjoy letting your thoughts drift gently through the strange questions that keep physicists awake, while hopefully helping the rest of us fall asleep, I would be ever so grateful if you gave the video a like and subscribed. It helps this little corner of calm science reach other curious travellers who might also need a peaceful place to rest their minds. And if you are already settled in, comfortable, and perhaps just beginning to feel that pleasant heaviness behind the eyes, then do not worry. Dark energy may be mysterious, but we shall approach it gently. No sudden noises, no frantic chalkboards, no equations leaping out from behind the curtains. Just the universe, quietly doing something strange. For a long time, humans thought of the cosmos as something mostly still. The stars seemed fixed, sprinkled across the night in familiar patterns. The moon changed, the planets wandered, comets made dramatic appearances now and then like guests who did not understand the dress code, but the great background of the heavens seemed steady. The universe, to the human eye, looked like a grand room with a very high ceiling. Then modern astronomy arrived and began politely rearranging the furniture. We learned that the stars were suns. We learned that the Milky Way was not the whole universe, but one galaxy among many. We learned that light takes time to travel, so looking deep into space is also looking back into history. And then we learned something even more astonishing. The galaxies are moving away from us, not because we are at the centre of some grand cosmic embarrassment, but because space itself is expanding everywhere. The distance between distant galaxies grows because the universe is stretching, rather like raisins in rising dough, though admittedly on a scale that makes even the most ambitious bakery seem modest. At first, this expansion seemed understandable. The universe had begun in an extremely hot, dense state, and it had been expanding ever since. Gravity, the great collector, the patient puller together of matter, would naturally try to slow that expansion down. After all, everything with mass attracts everything else with mass. Galaxies tug on galaxies, clusters tug on clusters. Matter says, in its quiet gravitational way, "Come back here, we were not finished." So the big question once seemed to be whether gravity would eventually win. Would the universe expand forever, gradually slowing but never quite stopping? Would it one day halt and collapse back inward? Or would it settle into some delicate balance, like a pencil standing on its point, impressive for a moment and then very unlikely to last? That was the expectation. The expansion might be fast, but gravity should be acting like a brake. Then, near the end of the 20th century, astronomers looked at very distant exploding stars and discovered that the universe had not been gently braking. It had been accelerating. The cosmic expansion was speeding up. Imagine tossing a ball into the air and expecting it to slow as gravity pulls it down, only to watch it rise faster and faster into the clouds, perhaps taking your hat with it. That is not the sort of thing one ignores. That is the sort of thing that makes scientists check the instruments, check the calculations, check the coffee, and then quietly realize that something very large has just become very strange. Those distant exploding stars were used like cosmic distance markers. They helped astronomers measure how far away galaxies were and how the expansion of the universe had changed over time. The result was shocking because it suggested that for billions of years the expansion had been speeding up. Space was not merely stretching. The stretching was becoming more urgent. So physicists gave the unknown cause a name: dark energy. This is an important point. Dark energy is not a substance that scientists have scooped into a jar. It is not a glowing mist floating between galaxies. It is not something we have directly touched, weighed, bottled, or asked to complete a questionnaire. It is a name for the mysterious cause of a measured effect. The effect is the accelerated expansion of the universe. The name is dark energy. The explanation is still the problem, and what a problem it is. The simplest idea is that dark energy might be a property of space itself. Empty space, in this view, is not truly nothing. It has a kind of built-in energy, a background tendency that does not dilute away as the universe expands. Matter thins out as space grows. Radiation stretches and weakens. But if dark energy belongs to space itself, then as more space appears, more of this energy appears with it. Not pouring in from somewhere else, not carried by little cosmic parcels, but present as part of the stage on which everything happens. This idea has a name in physics, though we will keep things verbal and gentle for now. It is often connected to a term Einstein once added to his theory of gravity, then regretted, then was later partly forgiven for. Einstein had introduced a kind of cosmic push into his equations when he wanted the universe to remain static. Later, when the expansion of the universe became clear, he reportedly considered the move a mistake. But physics has a mischievous memory. Sometimes the thing you put aside comes back decades later, wearing a different hat, and says, "Actually, you may still need me." That old idea returned because it behaves very much like the simplest version of dark energy, a steady energy of empty space, a constant cosmic pressure, a quiet feature of the universe that becomes more important as matter spreads out. There is only one small difficulty. When physicists try to connect this idea to what they know about quantum fields, the numbers become absurdly wrong. Not a little wrong. Not the sort of wrong where you have misplaced a decimal point and can still rescue the afternoon. More like the sort of wrong where your recipe for one biscuit accidentally produces enough dough to bury a continent. The expected value from one side of physics and the observed value from astronomy differ by an amount so enormous that it has become one of the most famous embarrassments in theoretical physics. And the universe, unhelpfully, continues expanding. This is part of why dark energy remains so puzzling. The simplest explanation works beautifully in many observations, but it does not sit comfortably with our deeper understanding of physics. It is as if the universe has handed us a key that opens the door perfectly, but the key is made of fog and hums suspiciously when no one is looking. Another possibility is that dark energy is not constant. Perhaps it changes over time. Perhaps it is caused by some field spread through space, something dynamic, something that evolves as the universe ages. This would make the story more complicated, but also potentially more revealing. If dark energy changes, then it may not be a simple property of empty space. It may be something with behavior, history, and maybe even surprises left to uncover. Recent surveys of galaxies have made this question even more interesting. Huge projects are mapping the universe in 3 dimensions, measuring how galaxies cluster, how cosmic structures grew, and how expansion changed across billions of years. Some results have hinted that dark energy might not be perfectly constant after all. Hinted is the careful word here. Science is not a place where one intriguing clue immediately becomes a finished answer, no matter how tempting that would be for headline writers and people who enjoy dramatic music. A hint is not a discovery. Attention is not a conclusion. A possible crack in the old picture is not yet a new picture. Still, these hints matter because they tell physicists where to look next. The universe may be whispering that the simple explanation is not the full story, or it may be reminding us that measurements are hard, galaxies are messy, and cosmic statistics can be a bit like trying to count sheep, while the sheep are several billion light years away and some of them may actually be goats. There is also the possibility that dark energy is not energy at all. Perhaps our theory of gravity, magnificent as it is, needs modification on the larger scales. General relativity has passed test after test, from the orbit of planets to the bending of light, from gravitational waves to black holes. It is one of the great achievements of human thought. But the universe is very large, and dark energy shows itself across the largest distances and longest stretches of time. Maybe gravity behaves differently there. Maybe what looks like a mysterious push is really a sign that our map of gravity is incomplete. That possibility is exciting, but it is also difficult. Any new theory has to explain the accelerated expansion without breaking all the things general relativity already explains so well. That is rather like trying to repair a watch while it is still ticking, while wearing mittens in the dark, with the watch being the size of the universe. So physicists find themselves in a curious position. They can measure the effect of dark energy with increasing precision. They can build telescopes, map galaxies, study supernovae, examine the oldest light in the universe, and compare the growth of cosmic structure across time. They can say, with impressive confidence, that something is causing the expansion of the universe to accelerate. But when asked what that something is, they must still answer with the most honest and powerful phrase in science. We do not know. There is a kind of beauty in that answer, even if it is not very tidy. We do not know is not a failure. It is an open door. It is the moment before a new idea. It is the reason instruments are built, careers are devoted, papers are written, and astronomers spend long nights coaxing faint light out of the dark. Science is not only a collection of facts, it is also a disciplined relationship with mystery, a way of standing before the unknown without inventing certainty just to feel more comfortable. And dark energy is mystery on the grandest possible scale. It is not hiding in some tiny corner of the cosmos. It is not an obscure detail, like the exact sleeping habits of a distant moon rock. Though I am sure those are fascinating in their own way. Dark energy appears to dominate the large-scale behavior of the universe. It shapes the future of cosmic expansion. It affects whether galaxies beyond our local neighbourhood will eventually drift so far away that their light can never reach us. It touches the deepest question of what kind of universe we live in and what kind of ending, if ending is even the right word, the cosmos may be moving toward. And yet, in everyday life, dark energy does not announce itself. It does not rattle the teacups. It does not tug at your socks. It does not make the kettle boil slower, though it would be convenient to blame it. You do not feel it because its effects are not local and dramatic. They are cosmic and cumulative. It is a mystery written across billions of years, visible only when we look at the universe as a whole. That contrast is part of what makes it so strange. The most powerful influence on the future expansion of everything is also almost completely absent from ordinary experience. We live inside a universe whose largest behaviour depends on something we cannot yet explain, while still needing to remember where we left the house keys. This is why the story of dark energy is not just a story about darkness, it is a story about measurement, about humility, about how the universe can surprise us after centuries of careful thought. It is about the way science advances, not by marching neatly from one answer to the next, but by noticing when something does not fit. A faint star is too dim, a galaxy is too far, a pattern is slightly off, a number refuses to behave, and from those small acts of noticing the entire picture changes. Tonight, we're going to follow that trail gently. We will begin with the moment astronomers realised the universe was not slowing down as expected, but speeding up. We will meet the exploding stars that acted as cosmic signposts, the old idea from Einstein that returned after being dismissed, the strange energy of empty space, the possible alternatives, the tensions in modern measurements, and the distant futures that dark energy may be preparing for the cosmos. But for now, settle in. Let your thoughts loosen a little. Let the day step back. Imagine the universe not as a fixed ceiling of stars, but as a vast, stretching ocean of space, carrying galaxies away from one another on a tide whose source we still cannot name. Somewhere in that expansion is a clue. Somewhere in the dark between galaxies is a question that has not yet finished asking itself. And somewhere, on a small planet around an ordinary star, we're listening, measuring, wondering, and trying, very gently, to understand why the universe is running away. For a long time, astronomers expected the universe to be doing something very sensible. It had begun expanding long ago, and gravity, being gravity, ought to have been slowing that expansion down, not stopping it necessarily, not grabbing every galaxy by the collar and dragging it back into one place, but at least gently applying the brakes. That was the reasonable picture. The universe had been flung outward in its hot beginning. Matter filled it, matter attracted matter, and so the grand expansion should have been gradually losing speed, like a bicycle coasting up a very long hill. This was not a foolish expectation. In fact, it was the obvious one. Gravity is attractive. It pulls things together. Stars form because gas clouds collapse. Planets orbit because gravity holds them in place. Galaxies gather in clusters because mass reaches across space and says, quietly but firmly, "Come this way." If you throw a ball upward, it slows as it rises. If you launch a rocket, you must fight the pull of the Earth. If you jump on a trampoline, even with great confidence and perhaps unwise enthusiasm, you do not simply continue accelerating into the ceiling. Gravity has opinions about that. So when astronomers looked at the expanding universe, the main question was not whether gravity would slow it down. The question was how much. Would the expansion slow gently and continue forever? Would it slow so much that one day it reversed, pulling all matter back into a final cosmic collapse? Or would it hover between those possibilities, expanding forever but only just, like a tired runner who technically has not stopped but would very much like a chair? This was the mood in cosmology before the discovery of dark energy. Scientists were trying to measure the deceleration of the universe. That word matters. Deceleration. They were not looking for acceleration. They were looking for the rate at which cosmic expansion was losing speed. It was a bit like setting up a speed camera on a quiet road because you expect the cars to be slowing down, and then discovering that every vehicle is calmly speeding up while no one is touching the accelerator. To measure the expansion history of the universe, astronomers needed distance, not just nearby distance, not the comfortable sort where you can say the shop is 5 minutes away and everyone understands roughly what you mean. They needed distances across billions of light years. They needed to know how far away galaxies were so they could compare that distance with how much the light from those galaxies had been stretched by the expansion of space. The stretching of light tells us how much the universe has expanded since the light began its journey. Distance tells us how long ago that journey began. Put those together carefully, and you begin to reconstruct the story of cosmic expansion. The trouble is that distance in astronomy is famously difficult. Space does not come with signposts. There is no helpful little marker halfway to a distant galaxy saying, "Welcome, you are now 3 billion light years from home. Refreshments available at the next nebula." Astronomers must build a ladder of measurements. Nearby distances help calibrate farther distances. Farther distances help reach still farther ones. Each rung depends on the one before it, and if one rung is wobbly, the whole climb becomes uncomfortable. One of the most useful tools for measuring great cosmic distances is a special kind of exploding star called a Type 1a supernova. These explosions are extraordinary. They occur when a dense stellar remnant known as a white dwarf reaches a critical state and undergoes a runaway thermonuclear explosion. That sounds rather violent for bedtime, and it is, but from the point of view of astronomy it is also wonderfully useful. These supernovae become incredibly bright. For a short time, a single exploding star can shine with the power of an entire galaxy. It is not subtle. It is the universe briefly switching on a lighthouse where a star used to be. The reason Type 1a supernovae became so important is that they have a useful pattern in their brightness. They are not all exactly identical, but their light can be standardized. By studying how the brightness rises and fades over time, astronomers can estimate how bright the explosion truly was. Once you know how bright something really is, and you compare that with how bright it appears from Earth, you can estimate its distance. It is the same ordinary logic you might use with a street lamp. If you know how powerful the lamp is, and it looks faint, then it is probably far away. If it looks bright, it is probably nearby. Of course, with supernovae, the lamp is an exploding star, the street is the universe, and the measuring tape is made of careful observation, patient analysis, and probably a worrying amount of coffee. By the 1990s, 2 independent groups were using these supernovae to measure the fate of the cosmos. One was known as the Supernova Cosmology Project, led by Saul Perlmutter. The other was known as the High Z Supernova Search Team, with key leadership from Brian Schmidt and major analysis work by Adam Rees. They were not setting out to discover something called dark energy. The phrase had not yet become the household name that it is in the very small number of households where people casually discuss cosmic acceleration over breakfast. They were trying to answer a straightforward question: how fast is the universe slowing down? The work was not glamorous in the way science sometimes appears in films. There were no glowing portals opening in the observatory dome. No one shouted that the laws of physics had collapsed while papers flew dramatically through the air. Much of the work involved planning observations, comparing images, hunting for tiny points of light that appeared where no point of light had been before, and then racing to study them before they faded. Supernovae are generous, but only briefly. They brighten, they peak, they dim. Miss the timing and the cosmic candle has already burned down. The search depended on a clever rhythm. Astronomers would take images of the same patches of sky weeks apart. Then they would compare the images, looking for new points of light. A galaxy that looked ordinary in one image might contain a sudden spark in the next. That spark might be a supernova. Once a candidate appeared, the teams needed follow-up observations quickly. They had to confirm what kind of supernova it was, measure its light curve, study its spectrum, and gather enough information to make it useful as a distance marker. It was careful work, repeated again and again, often at the mercy of telescope schedules, weather, instrument limits, and the simple fact that the universe does not always arrange its explosions at convenient hours. There is something charming about this. The discovery of cosmic acceleration, one of the most astonishing findings in modern science, depended partly on human beings comparing faint dots in the dark. The universe did not place a note on the door saying, by the way, expansion is speeding up. It sent light from exploding stars across billions of years and waited for someone to notice that the dots were a little too dim. That dimness was the key. When the distant supernovae were measured, they appeared fainter than expected. Not wildly fainter in a theatrical sense, not so faint that anyone could look once and say, yes, the universe is accelerating past the biscuits. The effect was subtle, but in precision astronomy, subtle can be enormous. The distant supernovae looked too far away for the kind of universe astronomers expected. If the expansion had been slowing down under gravity, those supernovae should have been closer and brighter. Instead, they were dimmer, which meant they were farther away. At first, this sounded like a problem with the data, and that is exactly how good scientists should react. A surprising result is not immediately a revolution. It is first an invitation to suspicion. Maybe the supernovae were not reliable distance markers after all. Maybe dust between galaxies was making them look dimmer. Maybe distant supernovae were different from nearby ones. Maybe the instruments had a calibration issue. Maybe something had been missed in the analysis. Maybe the universe was not being strange, and humans had simply made a mistake, which, to be fair, is not historically unheard of. So the teams checked. They checked the brightness measurements, they checked the colours of the supernovae. They checked the effects of dust. They checked whether the explosions might have evolved over cosmic time. They compared nearby and distant samples. They used different methods. They argued with the data in the quiet, professional way scientists do, which may involve less table flipping than one imagines, but still a great deal of determination. And the result would not go away. The supernovae were still too dim. The universe was still not behaving. The expansion, instead of slowing down, appeared to have started speeding up. Imagine for a moment what that must have felt like. You spend years designing a way to measure cosmic deceleration. You expect one of several answers, all of them involving gravity doing its familiar work. Then the data suggests the opposite, not merely a small correction, not just the universe is slowing a little less than expected, but something far stranger. The universe is accelerating. Space itself is expanding at an increasing rate. The galaxies are not just moving apart. The distances between them are growing faster as the universe ages. It is difficult to overstate how surprising that was. The 20th century had already made the universe stranger than anyone had expected. Space and time had become flexible. Matter had become quantum. Galaxies had become island universes. The cosmos had acquired a beginning, or at least a hot, dense early state from which it evolved. But even after all that, many scientists still assumed the large-scale fate of the universe would be governed mostly by matter and gravity. Dark energy changed the conversation. It suggested that the emptiness between galaxies was not merely passive. Something associated with space itself, or with a field spread through it, or with gravity acting differently than expected, was shaping the expansion of everything. The announcement did not instantly settle every question. Science rarely moves like a door slamming open. It moves more like dawn arriving through curtains, slowly then all at once. In early presentations and papers, the findings were discussed carefully. Other measurements were brought in, observations of the cosmic microwave background, the ancient afterglow of the early universe, would later support a picture in which the universe is spatially close to flat and contains much more than ordinary matter. Large-scale galaxy patterns also helped build the case. Piece by piece, the accelerating universe became harder to dismiss. Still, the supernova result was the spark. It was the moment astronomers realized that the cosmos was running away in a deeper sense than anyone had expected. Not running away from us specifically because we're not the center of the universe, however important the laundry pile on the chair may seem at the end of a long week. Every distant galaxy sees other distant galaxies receding. Expansion is not an explosion into empty space from one central point. It is the stretching of space itself. The space between galaxy clusters grows, the fabric of distance changes, and on the larger scales that change is accelerating. This can be a tricky idea because our everyday intuition is built for objects moving through space. A train moves along tracks, a bird moves through air, a biscuit moves from the plate to mysteriously somewhere near your mouth. But galaxies in an expanding universe are not simply flying through a pre-existing emptiness like sparks from a firework. On the larger scales, the space between them is growing. The galaxies are more like marks on the surface of an inflating balloon, each mark seeing the others move farther away as the surface stretches. No mark has to be the center. The expansion belongs to the whole surface. The supernovae showed that this stretching had changed over time in an unexpected way. In the early universe, matter was denser, and gravity was more influential in slowing expansion. But as the universe grew larger, matter became more spread out. Its gravitational pull over the cosmic expansion weakened. If dark energy remained roughly constant in space, then it would become more important as the universe expanded. Eventually it would dominate. The universe would shift from decelerating to accelerating. That transition is not just a detail. It is one of the great turns in cosmic history. There was a time when matter guided the pace. Then, slowly, the unknown influence we call dark energy took the wheel. No one watched this happen directly, of course. We infer it by looking across time. Distant supernovae are not merely far away. They are old messages. Their light began travelling when the universe was younger. Some of the photons that finally reach our telescopes have crossed space for billions of years, passing through a cosmos that changed while they were in flight. By collecting those messages from different distances, astronomers piece together a kind of cosmic diary. Here is how the expansion looked when the universe was younger. Here is how it looks later. Here is the strange bend in the story. There is a quiet patience in that method. We cannot pause the universe, rewind it, and measure it again from a better angle. We cannot build a second universe without dark energy as a control experiment, though one suspects funding agencies would have questions. We work with the light that arrives. We compare, correct, calibrate, and test. We let distant explosions become clocks and rulers. We use the death of stars to understand the life of the cosmos. When the discovery became accepted, it reshaped modern cosmology. The universe was no longer described only by ordinary matter, dark matter, radiation, and gravity. A new dominant ingredient had entered the model, or perhaps an old ingredient had been hiding in the equations all along. Dark energy seemed to make up most of the total energy budget of the universe. Ordinary matter, the stuff of stars, planets, people, kettles, and all known forms of cake, became a surprisingly small part of the cosmic inventory. Dark matter, already mysterious, made up more. But dark energy appeared to outweigh them both in its effect on the expansion of the universe. That is humbling. Everything we see with our eyes, everything that shines, everything familiar enough to touch, taste, or stub a toe against, is not the main component of the cosmos. Even dark matter, which already refuses to shine and must be inferred by gravity, is not the largest piece. The largest piece appears to be this smooth, strange influence driving accelerated expansion. It is rather like spending centuries studying the furniture in a room, only to realize that the room itself is quietly growing and nobody knows why. The scientists involved in the supernova discovery would later receive major recognition, including the Nobel Prize in Physics. But the recognition did not mean the mystery was solved. It meant the mystery had become unavoidable. The observations were powerful enough that physics had to respond. A universe speeding up cannot be treated as a footnote. It demands an explanation, and this is where the story becomes especially interesting. Discoveries in science often arrive with two emotions at once. There is excitement because something new has been found, and there is discomfort because the new thing does not fit neatly into the old understanding. Dark energy brought both. It gave cosmologists a clearer picture of the expansion history of the universe, while also confronting theorists with a question they still cannot answer cleanly. What is causing it? The simplest answer, the one that fits many observations remarkably well, is that dark energy is a constant energy of empty space. But that answer leads straight into another problem, because our best theories of tiny quantum fields seem to predict something wildly different from what astronomers observe. Other ideas suggest a changing field, or a modification of gravity, or some deeper feature of space-time that we have not yet understood. Each possibility has appeal, each has difficulties. The discovery of acceleration was not the end of the story. It was the beginning of a much harder one. That is often how the universe teaches. It does not always hand us a tidy explanation. Sometimes it offers a measurement so surprising that the explanation must be built slowly around it. A faint supernova here, a pattern in ancient light there. A galaxy survey spreading across the sky like a careful map of cosmic history. Each piece helps. None alone tells the whole tale. So when we say that astronomers found the cosmos was running away, we do not mean that galaxies are fleeing in panic, packing small galactic suitcases and refusing to answer our calls. We mean that the expansion of space is accelerating in a way that gravity from matter alone cannot explain. We mean that the universe, on the larger scales, is being shaped by something we do not yet understand. We mean that the night sky, which already looked vast enough, turned out to be part of a deeper and more unsettling motion. And perhaps that is why the discovery still feels so profound. It was not made by travelling to the edge of space. It was made by watching light, patiently, repeatedly, carefully. Light from stars that had destroyed themselves long before Earth received the news. Light that arrived faint, stretched, and carrying a message almost too strange to believe. The universe is not slowing as expected. The great distances are not merely growing, they are growing faster. From there, physics had to return to an older idea, one that had once been placed into the mathematics of gravity and then pushed aside. Einstein had introduced a term that could make space itself behave as though it had a built-in tendency to push against collapse. For many years it seemed unnecessary, even embarrassing. But after the supernovae, that forgotten idea began to look less like a mistake and more like a clue waiting patiently in the corner, perhaps sipping tea and trying not to look smug. That forgotten idea waiting quietly in the corner belonged, rather inconveniently, to Albert Einstein. And with Einstein, physics has a habit of becoming both clearer and stranger at the same time. He was not trying to discover dark energy. He was not trying to explain distant supernovae, because those observations were still many decades away. He was not sitting in his study thinking about the accelerating expansion of the universe while nibbling thoughtfully on toast. What he was trying to do was apply his new theory of gravity to the universe as a whole. That may sound like a natural thing to do. If you have just built one of the most powerful descriptions of gravity ever made, it is understandable to point it at everything and see what happens. But the universe, as usual, had other plans. Einstein had completed general relativity in the early 20th century, and it changed gravity from a force pulling across empty space into something deeper. Matter and energy shape the geometry of space and time, and that curved geometry tells matter how to move. It was a remarkable shift. The sun does not simply tug on Earth like a rope. The sun changes the shape of the space and time around it, and Earth follows a path through that curved geometry. This picture explained details that older gravity could not explain, and it gave scientists a new language for thinking about the cosmos. Gravity was no longer just a pull. It was the behaviour of space and time themselves. Then came the larger question. What happens if you apply this theory not to a planet, not to a star, not to light bending near the sun, but to the entire universe? At the time, the common assumption was that the universe was static. Not static in the sense that nothing inside it moved. Stars still moved, planets still orbited, gas clouds still drifted. Astronomers still had plenty to look at, and probably plenty to argue about. But on the larger scales, the universe was thought to be steady and unchanging. It had no overall expansion and no overall contraction. The Milky Way was often treated as the main cosmic system, and the idea of countless galaxies beyond it had not yet become the accepted picture. The universe seemed eternal, balanced, and mostly fixed. A grand cosmic room where the furniture might shift a little, but the walls were not moving. Einstein's equations did not naturally like that idea. When he tried to use general relativity to describe a universe filled with matter, the result was not a calm, static cosmos. Gravity pulled matter together. A universe filled with matter should either be changing, collapsing inward, or expanding outward, but not sitting perfectly still. This was a problem because Einstein, like many scientists of his time, believed the universe should be static. So he adjusted the theory. He added a new term, the cosmological constant, a built-in feature that could act against gravity on the larger scales. It was not designed to push apples off tables or make your socks leap out of the drawer. Its effect would matter over cosmic distances, where the entire universe was being considered at once. The purpose was balance. Matter pulled inward through gravity. The cosmological constant could provide a kind of outward tendency, just enough to hold the universe steady. Imagine trying to keep a heavy blanket stretched flat while gravity keeps pulling it into the middle. You might need someone gently tugging from the edges to stop it sagging. Einstein's added term played that role in his model. It was a cosmic adjustment, a way to make the universe remain still. That may sound like cheating, and in a sense many later physicists felt that it was. But it is worth being fair to Einstein. Scientists often work with the best observations and assumptions available at the time. The expanding universe had not yet been established. The data that would change everything had not yet arrived. Einstein was trying to make his theory fit what seemed to be the known universe, and the cosmological constant was not a random scribble in the margin. It was mathematically allowed within general relativity. The theory could include it. The question was whether nature actually used it. For a little while, the static universe seemed safe enough. But physics is rarely content to leave a tidy room undisturbed. Other scientists began finding different solutions to Einstein's equations. Alexander Friedmann showed that the equations allowed expanding and contracting universes. Georges Lemaitre, a Belgian priest and physicist, also developed the idea of an expanding universe and connected it with observations of galaxies moving away. Willem de Sitter explored models that showed strange cosmic behaviour even without ordinary matter in the usual sense. The mathematics was opening doors that the old static picture could not easily close. Then the observations arrived. In the 1920s, Edwin Hubble and others showed that many of the faint nebulae in the sky were not small clouds inside the Milky Way, but entire galaxies far beyond it. That alone was a huge expansion of human perspective. The universe was no longer just our starry neighbourhood. It was filled with other galaxies, each containing billions of stars. Then came the next shock. The light from distant galaxies was shifted in a way that suggested they were receding. The farther away they were, the faster they appeared to be moving away. The universe was expanding. That changed the role of the cosmological constant almost overnight. If the universe was already expanding, then Einstein no longer needed his added term to hold it still. The original reason for introducing it had vanished. The static universe was gone. The cosmic room did not have fixed walls after all. It was growing. Einstein removed the cosmological constant from his preferred model, and the term fell out of favour. Later stories say that he called it his biggest blunder. Whether that exact phrase came directly from him in precisely that form is a matter historians discuss carefully, but the message became famous. Einstein had added something to keep the universe static, and then the universe turned out not to be static. It is easy to smile at this. Einstein, of all people, making a cosmic mistake. It has a certain comforting quality, like seeing a great chef burn a piece of toast. But the story is more subtle than that. The real mistake may not have been adding the cosmological constant. The real mistake may have been adding it for the wrong reason, then dismissing it too completely once that reason disappeared. Because the constant itself never truly became impossible. It remained allowed by the theory. It was still there as a possibility, sitting quietly in the mathematical cupboard, perhaps next to the mysterious wizard bottle from earlier. For much of the 20th century, many physicists assumed the cosmological constant was zero, or so small that it did not matter. Cosmology had plenty of other problems to work on. The expanding universe, the origin of elements, the cosmic microwave background, the formation of galaxies, dark matter, black holes, quasars, and all the other cosmic surprises that arrived like guests who had not replied to the invitation. The cosmological constant was not completely forgotten, but it was often treated as unnecessary. If the universe could be explained without it, many preferred to leave it out. Physics likes simplicity, though it has learned the hard way that the universe does not always share that taste. Still, the term kept returning in certain situations. Sometimes it helped with puzzles about the age of the universe. Sometimes it appeared in theoretical discussions. Sometimes it was considered and then set aside again. It was not dead. It was more like a character in a long story who exits the stage, only to keep being mentioned by other characters, until you begin to suspect they may return in the final act wearing a new coat. Then came the supernova observations. When astronomers found that the expansion of the universe was accelerating, the cosmological constant suddenly became useful again. In fact, it became the simplest way to describe what was happening. If empty space itself has a constant energy, then that energy can drive accelerated expansion. It does not clump like matter. It does not gather into stars or galaxies. It remains smooth across space. And as the universe expands, it does not thin out in the same way matter does. Matter becomes more diluted because the same amount is spread through more space. Radiation weakens as space stretches. But a constant energy of space remains associated with space itself. More space means more of that space energy in the total cosmic accounting. This is a strange idea, so let us handle it gently. When we say empty space might have energy, we do not mean that space is secretly full of ordinary invisible gas or tiny dust, or a hidden ocean of glowing particles. Empty space, in modern physics, is not simply nothing. It has properties. It can stretch, it can curve, it can carry fields. Quantum theory suggests that what we call empty space still has activity at the smallest scales, although connecting that activity to the observed value of dark energy is one of the deepest problems in physics. The cosmological constant is the simplest description of a smooth, unchanging energy associated with space. It is not a detailed explanation of what that energy is. It is a clean way of describing how it behaves, and its behavior is unusual. Ordinary matter attracts through gravity and slows expansion. A cosmological constant acts differently. Its pressure has the effect of driving accelerated expansion. That sounds odd because pressure in daily life usually feels like something that pushes outward, only when it is inside a container. Air pressure pushes against the walls of a balloon. Steam pressure rattles the lid of a pot, which is one reason kettles and pans can seem more dramatic than necessary. But in cosmology, pressure contributes to gravity in a special way. A constant energy of space has a kind of pressure that makes the expansion speed up, rather than slow down. It is not pushing galaxies through space like a wind. It is changing the behavior of space itself. This is why the cosmological constant became such a natural suspect after the discovery of acceleration. It was already allowed by Einstein's theory. It matched the basic kind of cosmic acceleration being observed. It was smooth. It was simple. It did not require inventing a complicated new cosmic substance with a long list of awkward habits. In the language of modern cosmology, the simpler standard model includes ordinary matter, dark matter, radiation, and a cosmological constant. That model has been remarkably successful at describing many observations, from the pattern of the cosmic microwave background to the distribution of galaxies and the broad expansion history of the universe. But successful does not mean understood. This is the part that can be confusing. In science, a model can describe observations extremely well while still leaving the deeper cause unexplained. You can know how something behaves without knowing what it is. A clock can keep good time even if you have not opened the case. The cosmological constant is like that. It tells us how dark energy would behave if it is a constant property of space. It gives a simple mathematical description that fits a great deal of data. But it does not tell us why empty space has this energy, why the amount is so small but not zero, or whether it truly remains constant forever. That last question matters. If dark energy is exactly a cosmological constant, then its density does not change over time. It is steady. The future of the universe becomes relatively predictable in broad strokes. Distant galaxies continue drifting away faster as space expands. Structures not already bound by gravity eventually recede beyond view. The universe becomes colder, darker, and more spread out over immense times. Not tomorrow, of course, not next Tuesday, not even on timescales that make any difference to whether you remembered to put the bins out. But across cosmic ages, the effect becomes profound. If dark energy is not exactly a cosmological constant, then the story could be different. It might grow weaker. It might grow stronger. It might change with time in a way that tells us it is a field rather than a constant property of space. It might point to a modification of gravity. It might reveal that our current model is only an approximation, useful but incomplete. This is why physicists keep testing it. The cosmological constant is the simplest answer, but simplicity is not proof. The universe is allowed to be simple, but it is under no obligation to be polite about it. There is also the famous problem of its size. When physicists try to estimate the energy of empty space using ideas from quantum field theory, the result seems wildly larger than what cosmology observes, not a little larger. Not the kind of larger where one says, well, perhaps we used the wrong measuring spoon. The mismatch is enormous. It is often described as one of the worst prediction problems in physics. The observed value of dark energy is tiny in particle physics terms, yet large enough to control the future expansion of the universe. It is small enough to avoid tearing apart galaxies, stars, atoms, and afternoon tea, but significant enough to dominate the cosmos once matter becomes diluted. That combination is deeply puzzling. This is one reason Einstein's old term is both helpful and frustrating. It fits the observations in a simple way, but it does not explain itself. It sits in the model like a perfectly shaped missing piece, whose material nobody can identify. You can place it in the puzzle and see that the picture works better, but when you pick it up and ask what it is made of, it quietly refuses to answer. The history of the cosmological constant is therefore not just a story about one idea leaving and returning. It is a story about how physics treats assumptions. Einstein assumed the universe was static, so he added a term to make it static. Hubble's observations showed that the universe was expanding, so the term seemed unnecessary. Later, supernova observations showed that the expansion was accelerating, and the same term became useful again for a completely different reason. The object had not changed. The evidence around it had. That is a humbling lesson. A concept can be introduced for the wrong purpose and still turn out to describe something real. A discarded idea can return, not because scientists are indecisive, but because new observations change what the idea means. The universe does not care about our intellectual tidiness. It is perfectly happy to reuse an old tool in a new context, leaving humans to mutter into their notebooks. Einstein himself did not live to see the discovery of cosmic acceleration. He died decades before the supernova measurements made dark energy unavoidable. One wonders what he would have thought of the cosmological constant returning as a major part of modern cosmology. Perhaps he would have been amused, perhaps annoyed, perhaps both, which seems reasonable. After all, the term he reportedly regretted is now central to our best description of the universe. Not because the universe is static, but because it is accelerating. Not because gravity needed to be balanced into stillness, but because space itself may have a constant energy that shapes cosmic expansion. There is a gentle irony here. Einstein added the cosmological constant to stop the universe from moving. Modern physics uses it to explain why the universe is speeding up. The same idea that once held the cosmos still in theory now helps describe why the cosmos refuses to sit still in reality. That is not just ironic, it is wonderfully strange. And yet, we must be careful not to turn the story into a neat legend. It is tempting to say that Einstein predicted dark energy, then rejected it, then was proven right after all. That is too simple. He introduced a term that could act against gravity in a static model. Modern dark energy may be described by that same kind of term, but the physical interpretation is different. The old purpose was to maintain balance. The modern purpose is to explain acceleration. The connection is real, but the story is not a straight line. It loops, pauses, and doubles back, like someone looking for their glasses while already wearing them. This is often how deep science works. Ideas do not always arrive fully understood. They may begin as mathematical possibilities, then become physical hypotheses, then fall out of favour, then return with new evidence. A term in an equation can be ignored for decades, then become the doorway to a major mystery. What matters is not whether an idea has a dramatic history. What matters is whether it helps explain nature and whether it survives careful testing. So far, the cosmological constant survives remarkably well. It remains the leading explanation for dark energy because it is simple and effective. But physicists are not satisfied with simply naming it. They want to know whether it is truly constant. They want to know why it has the value it has. They want to know whether it emerges from quantum vacuum energy, from some deeper theory, from a new field, or from a misunderstanding of gravity on the larger scales. They want to know whether the universe is telling the simplest possible story, or whether the simple version is only what we can currently hear. The return of Einstein's old idea therefore leaves us in an interesting place. We have a name for the effect. We have a model that works. We have observations that support the broad picture of accelerated expansion. But the deeper nature of the cause remains hidden. The cosmological constant is not the end of the dark energy mystery. It is the most economical way of writing the mystery down. And the next clue comes from the light itself. The distant stellar explosions that first revealed the acceleration did not merely say that something strange was happening. They showed it through their brightness, their fading, their colour, and their distance. They became standard candles. Not perfect candles, not identical candles, but reliable enough to illuminate the expansion history of the cosmos. To understand why physicists believed the universe was accelerating, we need to follow that light more closely, from the moment a star destroys itself to the moment its faint message arrives in a telescope, long after the explosion has vanished into the dark. To understand why a faint point of light could change our picture of the entire universe, we need to spend a little time with one of astronomy's most useful ideas, the standard candle. It is a wonderfully homely phrase for something so cosmic. A candle is small, familiar, perhaps sitting on a bedside table or flickering on a kitchen shelf during a power cut, while a standard candle in astronomy may be a stellar explosion so bright that it briefly rivals a whole galaxy. Still, the principle is gentle enough. If you know how bright something truly is, and then you see how bright it looks from where you are, you can work out how far away it must be. A nearby candle looks bright. A distant candle looks dim. A very distant candle looks like it has become shy. This is the kind of reasoning our eyes use all the time without asking permission. A car headlight far down the road looks faint, then grows brighter as it approaches. A street lamp across a foggy park glows softly, not because it is weak, but because it is far away and its light is spread out before reaching you. If you were standing in a field at night and saw a familiar lantern glowing in the distance, you might not know the exact number of steps between you and it, but you would have a sense that dimmer means farther, provided you know the lantern itself has not changed. Astronomy takes that ordinary intuition and stretches it across the universe, which is quite typical of astronomy, really. It begins with something like a candle and ends with billions of light years, because apparently moderation is not a cosmic habit. The difficulty, of course, is finding objects in the universe whose true brightness we can know. Stars are not all the same. Some are small and cool, some are huge and hot, some are young and blue, some are old and red, some are unstable and dramatic as if they have just read a troubling email. If you see a faint star, it may be far away, or it may simply be a naturally faint star nearby. Without knowing its true brightness, you cannot use its apparent brightness as a reliable distance measure. It is like trying to guess the distance to a lamp without knowing whether it's a bedside bulb or a lighthouse. Astronomers have built many tools for measuring distances, each suited to a different range. Nearby stars can be measured using parallax, the tiny apparent shift in their position as Earth moves around the Sun. This is a beautiful method, but it only works well for relatively nearby objects. For farther galaxies, astronomers need brighter markers. Certain variable stars help. The patterns in their pulsing light reveal their true brightness, allowing them to serve as stepping stones to nearby galaxies. But to reach across truly enormous distances across the deep history of the universe, astronomers needed something brighter still. They needed explosions. And this is where Type 1a supernovae enter the story, politely at first, and then with the brightness of a catastrophe. A Type 1a supernova is the destruction of a white dwarf star. A white dwarf is the leftover core of a star that once lived a gentler, sun-like life. After such a star exhausts its fuel, sheds its outer layers, and settles into old age, it leaves behind a dense, hot remnant, roughly Earth-sized but containing a mass closer to that of the Sun. It is like compressing something enormous into something small, which is not recommended for luggage, but is fairly common in stellar evolution. A white dwarf is stable because it is supported by quantum pressure, a strange resistance that comes from the behaviour of electrons packed tightly together. It is not burning like an ordinary star. It is glowing with leftover heat, cooling slowly in the dark. But sometimes a white dwarf is not alone. Many stars live in pairs, orbiting a companion star in a long gravitational relationship that may be stable for ages and then suddenly become very eventful. If a white dwarf pulls matter from a companion, or if two white dwarfs come together, the white dwarf can be pushed toward a critical condition. Once it crosses that threshold, runaway nuclear burning can rip through it. The star does not merely flare up, it destroys itself. The result is a Type 1a supernova, a brilliant explosion that releases a tremendous amount of light and sends heavy elements into space. That may sound like a terrible ending for the star, and it is, but for astronomers it is also an extraordinary gift. Type 1. A supernovae have a useful consistency. They are not perfectly identical, because the universe rarely produces anything as conveniently uniform as a row of shop-bought candles, and even those somehow lean slightly to one side after dinner, but Type 1 a supernova can be standardized. Their light rises and fades in a pattern. By studying that pattern, especially how quickly the light declines after the explosion peaks, astronomers can correct for differences and estimate how bright the explosion truly was. This makes them standardizable candles, if we want to be especially careful, though standard candle is the phrase that has settled into common use. The light curve is the clue. A supernova brightens, reaches a peak, and then fades. Some fade more slowly, Some fade more quickly. The slower fading ones tend to be intrinsically brighter. By measuring this rise and fall, astronomers can refine the distance estimate. It is not as simple as saying every type 1a supernova has exactly the same brightness, but it is reliable enough with care to measure the expansion history of the universe, and care is doing a great deal of work in that sentence. Astronomers must account for dust, colour, the properties of the host galaxy, calibration of instruments, the stretching of time due to cosmic expansion, and many other details that would make an ordinary candle feel refreshingly uncomplicated. Now, imagine the practical challenge. A distant supernova appears in a galaxy billions of light years away. Its light has travelled for an enormous stretch of cosmic history before reaching Earth. By the time we see the explosion, the star has long since vanished. The light arrives faint, stretched and filtered through the expanding universe. Astronomers must detect it, identify it, measure its spectrum, follow how its brightness changes over time, and decide whether it belongs to the right kind of supernova. They are trying to read a message written in fading light, sent from a star that died before complex life on Earth may have looked up with anything like curiosity. No pressure then. The spectrum is especially important. By spreading the supernova's light into its colours, astronomers can identify the fingerprints of elements and determine what kind of explosion they are seeing. The spectrum also reveals redshift, the stretching of light caused by the expansion of the universe. As space expands, the wavelength of light travelling through it stretches too. Light from distant galaxies is shifted toward redder wavelengths. The greater the redshift, the more the universe has expanded since the light began its journey. Redshift is not just a colour change, it is a record of cosmic stretching. It tells us how much expansion the light has experienced along the way. So, with a Type 1a supernova, astronomers can get two crucial pieces of information. Its apparent brightness tells them its distance once the explosion has been standardized. Its redshift tells them how much the universe has expanded since the light was emitted. Compare these carefully for many supernovae at different distances, and a pattern emerges. That pattern is the expansion history of the universe. It is not a direct movie of cosmic expansion, but it is something close to a set of old photographs arranged in order. Each distant supernova shows the universe at a different age. Together they reveal how the expansion changed over time. This was the method that led to the discovery of accelerated expansion. Astronomers expected distant supernovae to show evidence of a universe slowed by gravity. If gravity had been putting the brakes on cosmic expansion, then very distant supernovae should have appeared brighter than they did in a universe with no slowing at all, because the expansion history would place them at a different distance for their redshift. That is the sort of sentence that sounds complicated, because the universe insists on stretching both light and patience. But the core idea is simple. The expected relationship between distance and redshift depends on whether the expansion is slowing, steady, or speeding up. The supernovae were the test, and the supernovae looked too faint. Fainter means farther, if the explosions have been properly standardized and no hidden effect is dimming them. The distant Type 1a supernovae appeared farther away than expected in a universe whose expansion was slowing. They were not where the old picture said they should be. Their light told a strange story. It suggested that the universe had expanded more than expected while that light was travelling. Space had stretched in such a way that the supernova ended up farther away from us than a matter-only, decelerating universe would predict. The expansion had not simply coasted under gravity's braking influence. At some point, it had begun accelerating. This was not a conclusion anyone wanted to accept too quickly. Type 1. A supernovae are powerful tools, but they are not magic. A dim supernova could mean distance, but it could also mean dust. Interstellar dust can absorb and redden light, making objects look fainter. If distant supernovae were hidden behind more dust than expected, perhaps they only seemed farther away. But dust leaves clues. It changes colours in particular ways. Astronomers examined the colours and spectra, and ordinary dust could not easily explain the effect. There was also the question of evolution. Were ancient Type I a supernovae exactly like nearby ones? The early universe had different stellar populations, different chemical histories, different environments. Perhaps distant supernovae were naturally fainter, not farther. That possibility had to be taken seriously. Astronomers studied host galaxies, compared nearby and distant events, refined their calibrations, and kept searching for signs that the candles themselves had changed. This remains an area of careful work even today. The standard candle is a powerful tool because it is tested, corrected, and tested again, not because scientists simply trust a cosmic explosion to behave itself without supervision. Instrument calibration mattered too. Measuring faint light from distant objects is not like glancing at a desk lamp. Detectors have quirks, telescopes have limits, atmospheres interfere when observing from the ground. Filters, exposure times, background light from host galaxies, and the details of image processing all affect the measurement. The teams hunting supernovae had to compare observations across instruments and nights and conditions. They needed to make sure the faintness was not a technical illusion. In astronomy, the universe is already difficult enough without the equipment joining in. And then there was the statistical challenge. One supernova would not be enough. A handful would not be enough. The case needed a population, many distant supernovae measured and compared. Each individual event carried uncertainties, but together a pattern could become clear. The original samples were small compared with modern surveys, but the signal was strong enough to start a revolution because two independent teams, working with different methods and data, found the same surprising trend. The distant supernovae were too faint. The expansion was accelerating. There is something deeply human in that moment. Imagine staring at the data and wanting the universe to be a little less strange. Imagine checking for dust, checking for mistakes, checking for hidden assumptions, perhaps checking the clock and wondering why scientific revolutions so often happen when everyone is tired. And then imagine the result remaining stubbornly there. Not an error, not a smudge, not a bad candle, a message. The message was not simply that distant stars explode. We knew stars could be dramatic. The message was that the geometry and history of the cosmos were different from what matter and gravity alone had led us to expect. The Type I, a supernova, became witnesses. Each one said, "I exploded long ago. My light travelled across expanding space. Measure me carefully, and I will tell you how far that expansion carried me." And when enough of them spoke, the universe seemed to be saying, "I am not slowing down anymore." The phrase standard candle can make the process sound almost quaint, as if astronomers are lighting little flames along the cosmic road. But these candles are violent deaths, brief and brilliant. Their usefulness comes from the fact that nature, in the midst of destruction, sometimes produces patterns. A white dwarf reaches instability. The explosion follows recognizable behavior. The light curve carries information. From chaos comes a ruler. From stellar ruin comes a measurement of cosmic destiny. That is one of the quiet wonders of astrophysics. The universe does not give us laboratory access to most of its grandest processes. We cannot put a galaxy cluster on a bench and adjust the settings. We cannot rerun the Big Bang with a slightly different recipe and see whether it rises better. We cannot ask dark energy to step forward and explain its qualifications, but we can use the events the universe already provides: supernovae, ancient light, galaxy clustering, gravitational lensing. The cosmos is not silent, it is just very indirect. Type Ia supernovae are still central to dark energy research, but they are no longer alone. Modern cosmology combines many probes. The cosmic microwave background gives us a view of the early universe. Galaxy surveys map how matter is distributed across vast distances. Baryon acoustic oscillations, which are fossil patterns from sound waves in the early universe, provide another kind of cosmic ruler. Weak gravitational lensing shows how mass bends the light from distant galaxies. Together, these tools build a more complete picture. Supernovae reveal the acceleration, but other observations help test and refine the model. This matters because the dark energy question is no longer only whether the universe is accelerating. It is what kind of acceleration it is. Is dark energy truly constant, the same across time and space? Or does it evolve? Does it behave like Einstein's old cosmological constant, or like a field slowly changing through cosmic history? Are the measurements all pointing to one simple answer, or are there small tensions telling us the story is more complicated? Every new survey tries to sharpen the picture. More supernovae, better calibration, wider sky coverage, deeper observations, less room for hidden errors, more room, perhaps, for surprises. The light from supernovae also reminds us that the discovery of dark energy was not a single bright flash of understanding. It was a careful accumulation. A faint point appears in a galaxy. It is measured. It fades. Its spectrum is analysed. Its host is studied. Its redshift is determined. It is placed on a diagram with others. One point becomes many. Many become a pattern. The pattern becomes a challenge to theory. The challenge becomes a new picture of the universe. Science at its best is patient enough to let the faint things speak. There is a lovely contrast here. Dark energy is vast and smooth. If the simplest model is right, spread across all of space and shaping the destiny of the universe. A Type 1a supernova is brief, local, explosive, and bright. One is quiet and everywhere. The other is violent and temporary. Yet the temporary explosion revealed the quiet influence. A star died, and in its fading light we noticed the universe accelerating. The story also teaches caution. Standard candles are not perfect candles. Every improvement in the data asks whether the old conclusions still hold. Are there subtle differences between supernovae in young and old galaxies? Does dust behave exactly as assumed? Are local measurements calibrated correctly? Do different samples agree? These are not annoyances. They are the machinery of trust. A result becomes strong not because no one questions it, but because it survives being questioned from every angle scientists can think to try. The accelerating universe has survived many such tests, though the details of dark energy remain open enough to keep cosmologists very busy and possibly over-caffeinated. And so, when we picture those distant supernovae, it helps not to imagine them as simple cosmic lamps, but as messengers. Each one carried a message written in brightness and colour, stretched by expansion, dimmed by distance, and delivered after billions of years to mirrors and detectors on a small planet. The message was not loud. It was not obvious. It had to be decoded. But once decoded, it changed everything. The universe was not merely expanding from a hot beginning. It had entered a phase in which expansion was speeding up. Gravity had shaped the early contest, pulling matter into galaxies, clusters and filaments, building the web of structure we observe across space. But as the universe grew, matter thinned. Its grip on the overall expansion weakened. Something else became important. Something smooth, persistent, and still not understood. The supernovae did not tell us what that something was. They told us that it had to be taken seriously. That is why the next difficulty is so deep. If dark energy behaves like a constant energy of space, then perhaps it is connected to the vacuum itself, to the strange, not quite empty emptiness described by quantum physics. But when physicists try to make that connection, the numbers do not merely misbehave, they become almost comically unreasonable. The candles showed that the universe is accelerating. The old cosmological constant gave a simple way to describe it. Then quantum theory walked into the room, looked at empty space, and somehow produced one of the most embarrassing disagreements in modern physics. Empty space has a reputation for being simple. It sounds like the easiest thing in the universe to understand, really. Take away the stars, take away the planets, take away the gas, the dust, the galaxies, the comets with their dramatic tails, and whatever remains should be nothing. A calm absence, a clean stage, a cosmic room after everyone has gone home and someone has turned off the lights. But physics has a long history of taking words that seem simple and making them quietly difficult. Empty is one of those words, so is nothing, so is vacuum. In everyday life, a vacuum means you have removed as much air as you can from a container, perhaps with a pump, or with a machine that makes an alarming noise in the hallway, while refusing to pick up the one crumb you're actually aiming for. But in modern physics, the vacuum is not merely emptiness. It is the lowest energy state of fields that exist everywhere. It is what remains when you have removed every particle you can remove, and yet the underlying fields are still there. That is already a strange thought. According to quantum field theory, the world is not made only of little particles moving through space like tiny beads in a box. Instead, each kind of particle is associated with a field spread throughout space. Electrons are excitations of an electron field. Photons are excitations of the electromagnetic field. Other particles belong to other fields. A particle is like a ripple on a field, and the field itself does not disappear simply because there are no ripples visible at the moment. The surface may look calm, but the underlying thing is still present. This means that even what we call empty space is filled with fields, not filled in the ordinary cluttered sense like a cupboard where someone has pushed in too many mugs, filled in a more basic way. The fields are part of the structure of physical reality. They are there before particles appear and after particles vanish. And quantum theory tells us that these fields cannot be perfectly still. There is always a minimum amount of activity, a restless low-level jitter that comes from the uncertainty built into the quantum world. That little word jitter can be misleading because it sounds harmless, like a sleepy hand reaching for a teacup before the brain has fully joined the morning. But the quantum vacuum is one of the most important and puzzling ideas in physics. It is not empty in the old sense, it has measurable effects. In laboratories, physicists have seen evidence that the vacuum changes the behavior of particles and forces. There are phenomena where empty space between objects affects them in subtle ways. The vacuum is not nothing, it is a physical state with properties. So when cosmologists ask whether dark energy might be vacuum energy, they are not simply inventing something from nowhere. They are looking at two ideas that seem, at first glance, to belong together. On one side, astronomy says the expansion of the universe is accelerating, and the simplest model describes this as a constant energy associated with space itself. On the other side, quantum field theory says empty space is not truly empty and should have energy. It feels natural to connect them. Perhaps dark energy is simply the energy of the vacuum. Perhaps the universe is accelerating because empty space carries a tiny but persistent energy that becomes important only across cosmic distances. It is a tidy thought, almost too tidy. And in physics, when something feels that tidy, it is wise to check under the carpet. The difficulty comes when physicists try to estimate how much vacuum energy should exist. Quantum fields have many possible modes of vibration, rather like a musical instrument with an enormous number of possible notes. Even in the vacuum state, those modes contribute some amount of energy. If gravity responds to all forms of energy, as general relativity tells us it should, then vacuum energy should help curve space and affect cosmic expansion. So the question seems straightforward. What value does quantum theory predict, and what value does the universe appear to have? And this is where the room becomes very quiet. The observed dark energy density is extremely small. Not zero, because the universe appears to be accelerating, but small. Astonishingly small by the standards of particle physics. It is gentle enough that it does not tear apart galaxies, stars, planets, atoms, or the biscuits you may have set aside for later. It matters only over enormous cosmic distances and enormous stretches of time. Locally, gravity, electromagnetism, and the other forces dominate ordinary life. Dark energy is not pushing your chair away from the desk or making your socks separate in the wash, although one should never rule out household mysteries too quickly. But when theoretical physicists make a rough estimate of vacuum energy from quantum fields, they do not get a tiny cosmic whisper. They get something absurdly large. Depending on how the estimate is made, the expected value can be larger than the observed value by an almost unimaginable amount. This mismatch is often called the cosmological constant problem. It has also been called the vacuum catastrophe, which sounds like something that happens when you accidentally use the wrong attachment on a carpet, but is in fact one of the deepest conflicts between our understanding of the very small and our understanding of the very large. The reason it is sometimes described as the most embarrassing number in physics is not because physicists are easily embarrassed, although after a few decades of a problem refusing to leave, anyone might begin to feel a little awkward. It is because the mismatch is so extreme. The theory that works brilliantly for particles and fields seems, when naively connected to gravity and the expansion of the universe, to predict a vacuum energy vastly larger than what the cosmos permits. If that predicted energy really gravitated in the expected way, the universe would not look anything like the one we observe. It might have expanded violently beyond recognition, or curved in a way that left no room for galaxies, stars, or anyone to sit quietly wondering about it. And yet here we are. That is the puzzle. Quantum field theory works with extraordinary accuracy in its own domain. General relativity works with extraordinary accuracy in its own domain. Cosmology, built from observations of supernovae, galaxy clustering, the cosmic microwave background and other evidence, gives us a small but non-zero dark energy. Each part of the picture is successful, but when we try to place the parts together, the vacuum energy becomes a problem. The pieces do not meet cleanly. It is like building 3 sides of a cabinet perfectly, then discovering that the final side thinks it is a cathedral. Physicists are careful about this problem because the simple popular version can hide technical subtleties. Calculating vacuum energy is not as straightforward as pouring numbers into a bowl and stirring until a universe appears. There are issues of renormalization, cutoffs, symmetries, phase transitions, and how energy should be treated in quantum field theory when gravity is involved. Some contributions might cancel others. Some values may not be physically meaningful until compared in the right way. The vacuum in particle physics is not a little battery sitting in space with a neat label on it. It is part of a very sophisticated mathematical framework. But even with all those cautions, the problem does not vanish. The observed cosmological constant is extraordinarily small compared with known energy scales in particle physics. It is not obvious why the various contributions to vacuum energy should cancel so precisely, leaving behind just the tiny amount required to match cosmic acceleration. This is sometimes called a fine-tuning problem. It is as though many enormous numbers are being combined, and after all the additions and cancellations, the leftover is a tiny value balanced with absurd delicacy. Like stacking a tower of teacups to the moon and having the top one land exactly upright on a saucer in your kitchen. That kind of delicate cancellation makes physicists suspicious, not because nature cannot be delicate, but because unexplained delicacy often points to something missing. If a number must be tuned with extraordinary precision to match observations, scientists begin to ask why. Is there a symmetry forcing it to be small? Is there a mechanism that cancels it? Is our assumption about how vacuum energy gravitates wrong? Is dark energy not vacuum energy after all? Or are we interpreting the problem from the wrong theoretical viewpoint? One idea is that there may be a symmetry in nature that naturally cancels vacuum energy. Symmetries are powerful in physics. They explain conservation laws and organize the behavior of particles. A certain kind of symmetry, if exact, could help cancel contributions from different fields. But the symmetries we know are not exact in the needed way, at least not in the world we observe. If a symmetry nearly solves the problem but then breaks, the remaining vacuum energy is still generally much too large. The universe, inconveniently, seems to have left the value very small but not zero, which is exactly the sort of answer that keeps theorists awake while pretending they are just making tea. Another possibility is that there is a dynamical mechanism. Perhaps the vacuum energy relaxes over time, adjusting itself toward a small value. Maybe some field evolves in such a way that the large contributions are reduced. This is an appealing thought because it turns the strange number into the result of a process rather than an accident. But it is hard to build such mechanisms without causing other problems. The field must change the vacuum energy without disrupting the early universe, the formation of galaxies, the behavior of gravity, or the many precise observations that already match our current model. It is rather like trying to quietly remove a squeaky floorboard during a concert without anyone hearing, while the floorboard is connected to the stage, the orchestra, and possibly the roof. Some physicists look to the idea of a multiverse. In certain speculative theories, there may be many regions or many possible universes with different values of vacuum energy. Most values would not allow galaxies or observers to form. If the vacuum energy were too large and positive, space might expand too quickly for matter to gather into galaxies. If it were too negative, the universe might collapse too soon. In that picture, we observe a small value, because only regions with a suitable value can contain observers asking questions about it. This is called anthropic reasoning. It is controversial, partly because it can feel less satisfying than a mechanism. It does not say the value must be what it is because of a simple law. It says we find ourselves in a place where the value permits our existence. Some scientists take that idea seriously, others find it uncomfortable. Physics has often succeeded by finding deeper principles rather than accepting that a parameter is what it is, because otherwise we would not be here. Yet the cosmological constant problem is so stubborn that even uncomfortable ideas remain part of the conversation. When a mystery refuses to move for long enough, physicists begin checking doors they might otherwise have walked past. There is also the possibility that dark energy is not vacuum energy. Perhaps the acceleration is caused by a new field, something slowly changing over time. This would mean the observed cosmic acceleration is not the fixed energy of empty space, but a dynamic ingredient. That kind of idea has many names and variations, and it leads naturally into other suspects in the dark, but it must still explain why the field behaves in just the right way, why it is so smooth, why it became important only relatively recently in cosmic history, and why it has not already shown up through other effects. That last point is another puzzle, often called the coincidence problem. Dark energy became dominant only after matter had thinned out enough during cosmic expansion. Early on, radiation and matter controlled the universe's behavior. Later, as space expanded, matter became diluted while dark energy, if constant, stayed the same per volume of space. Eventually, dark energy overtook matter as the main influence on expansion. But why now, cosmically speaking? Why should we live during the era when matter and dark energy densities are close enough that both are relevant to the cosmic story? In the distant past, dark energy was negligible. In the far future, it may utterly dominate. We appear to live during the interesting transition. Of course, every era thinks it is interesting. Ask a dinosaur, and it might have strong feelings about the late Cretaceous, at least before the asteroid discussion begins. But in cosmology, the coincidence is real enough to bother people. It may simply be chance, or it may be a clue that dark energy is linked to cosmic evolution in a deeper way. The vacuum energy problem also reveals something profound about the unfinished marriage between quantum theory and gravity. Quantum field theory describes particles and fields against the background of space and time. General relativity says space and time are not merely a background. They respond to energy and matter. Put those ideas together, and the vacuum should gravitate. But we do not yet have a complete quantum theory of gravity. Perhaps the right theory changes how vacuum energy contributes to the curvature and expansion of the universe. Perhaps the problem looks impossible only because we're using tools that work well separately but not together at the deepest level. This is not an excuse. It is a map of our ignorance. And science, at its best, makes good maps of ignorance. It marks where the roads end, where the cliffs are, where the signs become smudged and someone has written probably dragons in the margin. Dark energy sits near one of those margins. It connects cosmology, gravity, quantum fields, particle physics, and the fate of the universe. That is why the problem is so difficult. It is not one mystery in one field. It is a knot tied between several of our best theories. Still, the smallness of dark energy is also what allows the universe to be rich. If vacuum energy were enormously larger, structures might never have formed. Galaxies require time. Gas must gather. Stars must ignite. Heavy elements must be made and spread. Planets must form from the leftovers. Chemistry must become complicated. Life, if it appears, does not seem to enjoy being hurried. A universe dominated too early by a huge vacuum energy would expand so fast that matter could not clump into the cosmic architecture we see. The fact that dark energy is tiny is not just a numerical irritation. It is part of why there is a universe with history, structure, and quiet creatures capable of measuring supernovae. So the embarrassing number is also a strangely generous number. It is small enough to permit galaxies, but large enough to reveal itself in the late-time expansion. It hides through most of local physics, then announces itself across the largest distances. It avoids the laboratory spotlight, but shapes the cosmic stage. It is the softest possible shove with the largest possible consequences. This brings us back to the word vacuum. We began with empty space, expecting it to be simple. Instead, it may be the source of the dominant influence on the universe's expansion. Or it may be hiding a problem that tells us dark energy is something else entirely. Either way, emptiness is not empty in the way our intuition wants it to be. Space is not merely the gap between objects. It has properties. It can stretch, curve, carry fields, and perhaps possess energy. The nothing between galaxies may be one of the most important somethings in physics. And yet, after all that, the honest answer remains unsettled. Vacuum energy is the most straightforward candidate for dark energy, but it brings with it the cosmological constant problem, the fine-tuning problem, and the coincidence problem. It explains the observed acceleration in a simple model, but it refuses to fit comfortably with the deeper theoretical machinery beneath it. The result is a strange scientific situation. The simplest explanation works very well observationally, while making theorists deeply uneasy. It is like finding a key under the mat, watching it open the door perfectly, and then realizing the key is made from a material that should not exist. That unease is productive. It pushes cosmologists to measure dark energy more precisely. It pushes theorists to search for mechanisms, symmetries, new fields, modified gravity, and deeper principles. It asks whether the vacuum truly has energy, whether that energy gravitates in the expected way, whether the cosmological constant is fundamental, or whether it is only an effective description of something more subtle. The embarrassment is not the end of the story. It is the sign that the story has reached a place where our best ideas are touching something they cannot yet explain. And once physicists admit that dark energy might not be simple vacuum energy, a new set of possibilities comes into view. Perhaps the darkness is not constant. Perhaps it changes slowly. Perhaps it's carried by a field rolling through cosmic history, or by an energy that grows stranger with time. Some ideas are elegant, some are speculative, and some sound as though they were named by people who had spent too long in a seminar room without fresh air. But each begins with the same question left behind by vacuum energy. If empty space is not the whole answer, then what else could be driving the universe apart? If empty space is not willing to explain itself, physicists must begin interviewing other suspects. This is where the dark energy mystery becomes a little like a cosmic detective story, although a very slow one, with fewer footprints, more telescope time, and no convenient butler standing in the drawing room looking nervous. The simplest suspect is still the cosmological constant, the steady energy of empty space that behaves the same everywhere and everywhen. It fits a great deal of what we observe. It is tidy, it is efficient. It sits in the equations with the calm confidence of someone who has arrived early to a meeting and brought their own pen. But a tidy suspect is not always the guilty one. The problem, as we have seen, is that vacuum energy raises difficult questions. Why is it so small? Why is it not zero? Why did it become important only after the universe had already spent billions of years forming galaxies and stars? And why does it fit observations so well, while making theorists feel as though they have found a perfectly baked cake in an oven that was never turned on? The cosmological constant may be correct, it may be the final answer, but because it leaves such deep, theoretical puzzles behind, physicists have spent decades asking what else dark energy might be. One of the most famous alternatives is called quintessence. It's a rather elegant name, borrowed from an old idea that the heavens were made of a fifth essence beyond earth, water, air, and fire. Modern quintessence is not that ancient substance, of course. There is no shimmering celestial fluid drifting between the planets like a mythological soup. In cosmology, quintessence usually means a new field spread throughout space, one that changes slowly over time and can drive accelerated expansion. Instead of dark energy being a fixed property of empty space, it would be something dynamic, something with a history. A field may sound vague, but fields are standard tools in modern physics. The electromagnetic field is real. It fills space and produces light, radio waves, magnetism, and the small, everyday miracle that your phone can communicate without a tiny person carrying notes through the air. Other fields are associated with particles. The Higgs field gives certain particles mass. Fields are not exotic decorations added because physicists enjoy complicated furniture. They are part of the usual language of nature. So it's not unreasonable to ask whether dark energy could also come from a field. The appeal of quintessence is that it can change. A cosmological constant stays the same. It does not evolve, weaken, strengthen, or have moods. Quintessence, by contrast, can roll gradually through cosmic time. The word roll here is a metaphor, but a useful one. Imagine a marble moving slowly across a very broad, shallow landscape. If the landscape is arranged just right, the field changes so slowly that its energy acts much like dark energy, gently causing expansion to accelerate. But because it changes, it might leave traces in the history of the universe. It might have been slightly different billions of years ago. It might become different in the future. It might help explain why dark energy began dominating only relatively recently, instead of being equally important throughout cosmic history. That would be helpful, because the timing is suspicious. In the early universe, radiation dominated. Later, matter dominated. Galaxies formed during this matter-ruled era, gathering gas, making stars, building clusters and filaments. Dark energy, if it behaves like a cosmological constant, was present all along but too weak to matter much at first. Only after matter had thinned out enough did dark energy become the main influence on expansion. The question is why that happened around the era when galaxies, stars, planets, and curious mammals with telescopes could exist. It may be coincidence. The universe is allowed coincidences, even large ones. But physicists prefer to ask whether coincidence is hiding mechanism. Quintessence offers one possible mechanism. If dark energy comes from a changing field, then its importance may naturally grow or shift over time. It might track the background behavior of the universe for a while, then begin to dominate later. Some versions are called tracker models because the field follows the dominant cosmic component before gradually taking over. The attraction of these models is that they can reduce the feeling of fine-tuning. Instead of needing dark energy to be placed at exactly the right tiny value from the beginning, perhaps the field evolves toward a suitable value as the universe ages. That sounds promising. But every promising idea in cosmology must pass through a rather narrow doorway. It has to explain the accelerated expansion, match the cosmic microwave background, allow galaxies to form properly, agree with supernova observations, fit galaxy clustering, avoid disrupting the early universe, avoid producing forces we would already have detected, and generally not knock over the carefully stacked tower of evidence already supporting modern cosmology. This is the scientific equivalent of asking a guest to enter the room quietly, sit down, help solve the mystery, and please not step on the cat. Quintessence has difficulties. The field must be extremely light and smooth over vast distances. If it interacts too strongly with ordinary matter, it could create a new force, something beyond the known forces, and experiments on Earth or observations in space might already have seen its effects. If it changes too quickly, it would not look like the dark energy we observe. If it changes too slowly, it becomes hard to distinguish from the cosmological constant. That is one of the frustrating things about many dark energy models. The more carefully they are adjusted to fit observations, the more they can begin to resemble the simple model they were meant to replace. It is like buying a new chair because the old one creaks, then discovering the new one looks exactly the same but has a more complicated instruction manual. Still, quintessence remains important because it gives physicists a way to test whether dark energy evolves. If future observations show that dark energy has changed over time, even slightly, that would be a major clue. It would suggest that the cosmological constant is not the whole story. It would point toward a dynamic ingredient, perhaps a field. This is why large surveys of galaxies and supernovae are so valuable. They are not merely checking whether the universe expands, they are trying to reconstruct how that expansion changed over billions of years. A tiny deviation from constant behavior could open a door. Then there is phantom energy, which sounds as though it should come with a candlelit corridor and a warning from a local villager. Phantom energy is a more extreme idea. It describes a kind of dark energy, whose influence grows stronger as the universe expands. With a cosmological constant, the density of dark energy stays the same as space grows. With ordinary matter, density decreases because matter spreads out. Phantom energy does something stranger. Its effective density increases with expansion. The more the universe grows, the more dominant this energy becomes. That is a deeply unsettling possibility, not because it affects your evening routine, but because of what it could mean for the far future. If phantom energy grows stronger without limit, it could eventually overcome not only the gravity holding galaxy clusters together, but galaxies themselves, then solar systems, then planets, and in the most extreme scenario, even atoms. This hypothetical future is known as the Big Rip. It is exactly as cheerful as it sounds. First, the larger structures would be torn apart. Later, smaller bound systems would follow. Eventually, if the model is pushed all the way, everything would be pulled apart by the accelerating expansion. Now, before anyone sits up in bed and becomes concerned about being cosmically shredded before breakfast, it is worth being clear. The Big Rip is speculative. It depends on dark energy behaving in a very particular phantom-like way. Current observations do not require that future. They allow the cosmological constant quite well, and many evolving models do not lead to anything so dramatic. The Big Rip is not a forecast for next week. It is an example of how different dark energy behavior could produce very different cosmic endings. It is a reminder that the nature of dark energy is not just a question about what is happening now, it is a question about the destiny of everything. Phantom energy also has theoretical problems. In many simple forms, it behaves in ways that make physicists nervous. It can lead to instabilities, meaning the theory may not be well behaved when examined deeply. A model is not enough if it fits the expansion history, but breaks the underlying rules that make physical theories reliable. A dark energy candidate must not only match observations, it must also make sense as a piece of fundamental physics. Otherwise, it is more like a clever costume than a real suspect. There are also models that try to cross between ordinary quintessence-like behavior and phantom-like behavior. These can be more flexible, and flexibility can be useful when fitting data. But flexibility is dangerous too. A model with many adjustable features can fit almost anything. the way a blanket can be tucked around any oddly shaped object if you keep folding long enough. Physicists prefer models that explain more with less, models that make clear predictions and can be tested. A theory that can adapt to every possible observation may be comfortable, but it is not always informative. Another suspect is early dark energy. This idea suggests that dark energy may not have been completely negligible in the early universe. Perhaps a small amount of dark energy affected the universe before the formation of the cosmic microwave background, or during the era when the first large-scale patterns were being established. Early dark energy has attracted attention partly because it might help with certain measurement tensions in cosmology, especially disagreements about the present expansion rate. But it is difficult to make it work cleanly. If too much early dark energy is present, it changes the ancient light of the universe in ways we would notice. If too little is present, it may not solve the problem it was introduced to address. Like many ideas in cosmology, it must walk a narrow path between usefulness and trouble. There are also coupled dark energy models, where dark energy interacts with dark matter. Since both are dark, mysterious, and known mostly through their cosmic effects, it is tempting to wonder whether they might be connected. Perhaps dark matter and dark energy are not completely separate ingredients. Perhaps energy is exchanged between them. Perhaps the dark sector has its own hidden physics, invisible to ordinary matter but important on cosmic scales. This is an intriguing possibility because it might explain why dark matter and dark energy densities have the relationship they do today. But it is also difficult because interactions between them would change how cosmic structure grows, how galaxies cluster, and how the expansion unfolds. Observations place tight limits on such behaviour. Then come models with names like K-essence, chameleon fields, and other variations that sound as though cosmologists have occasionally allowed fantasy novelists to label their notebooks. K-essence is a type of dynamic dark energy, where the field has unusual motion properties. Chameleon fields are designed to hide their effects in dense environments, like Earth or the solar system, while becoming important in the emptier regions of space. The name chameleon is fitting because the field changes its behaviour depending on its surroundings. This helps explain why a new field might affect the universe on large scales without showing up in local experiments. It is the cosmic equivalent of someone who is very loud at a party, but perfectly silent whenever a parent walks into the room. These screening mechanisms are clever. They allow modified fields or modified gravity to avoid local detection, while still influencing cosmic expansion. But cleverness is not enough. The mechanisms must be mathematically consistent, stable, and compatible with many observations. They must match the motion of planets, the behaviour of light near massive objects, the growth of galaxies, the cosmic microwave background, and the expansion history. Nature has left many traps for theories that try to hide. A model may conceal itself in one place only to reveal itself somewhere else, rather like trying to sneak biscuits from the kitchen and forgetting the packet makes noise. Modified gravity is another major suspect. Maybe there is no dark energy substance or field at all. Maybe the acceleration tells us that gravity behaves differently on the larger scales. General relativity has been tested beautifully in many environments, from the solar system to black holes and gravitational waves. But dark energy appears on cosmic scales, across the largest distances and longest times. Perhaps general relativity is not wrong exactly, but incomplete in this domain. A modified theory of gravity might reproduce the successful predictions we already have while adding new behaviour that looks like cosmic acceleration. This possibility is attractive because it attacks the problem from a different direction. Instead of asking what invisible energy is pushing the universe apart, it asks whether our understanding of gravity needs revision. After all, the acceleration is inferred through gravity and expansion. If the rules of gravity change over huge distances, maybe the effect we call dark energy is really a clue about gravity itself. But this is a hard route. General relativity is not easy to improve. It is elegant, powerful, and extremely well tested. Any modification must keep the successes while explaining the new observations. That is like rewriting a beloved book without changing any of the lines people already quote, while somehow adding a missing ending everyone agrees was needed. One way to distinguish dark energy from modified gravity is to compare expansion with structure growth. Dark energy affects how the universe expands. Gravity affects how matter clumps. In the standard picture, these are linked in a predictable way. If observations show an expansion history that points one way, but the growth of galaxies and clusters points another, that could suggest modified gravity or some more complicated dark energy behaviour. This is why galaxy surveys do more than measure distances. They also map the cosmic web. They study how matter is gathered over time. They look for the fingerprints of gravity in the arrangement of galaxies. A true cosmological constant is smooth and simple. It changes expansion but does not clump into structures. Quintessence is usually also very smooth, though it can evolve with time. Some modified gravity models change how structures grow. Some interacting dark energy models alter the distribution of matter. Each suspect leaves a slightly different trail. The problem is that the trails are faint, overlapping, and partly hidden by observational uncertainty. The universe is not a clean crime scene. It is more like a very old attic full of dust, mirrors, and boxes labelled miscellaneous. Recent galaxy surveys have made the situation more interesting by suggesting that dark energy might not be perfectly constant. The word might is doing important work here. Some combinations of data have hinted at evolving dark energy, while the standard cosmological constant model remains highly successful and has not been overthrown. Cosmology is full of tensions that may become discoveries, and also full of tensions that may fade with better data. A hint is not a verdict, but hints are valuable because they tell us where to look more carefully. If dark energy evolves, the next generation of observations should make that clearer. If it does not, the cosmological constant will become even harder to escape. This is the strange position physicists now face. The simplest suspect remains the strongest, yet the alternatives are too important to ignore. Quintessence offers change. Phantom energy offers extreme futures. Early dark energy offers possible clues to early universe tensions. Coupled dark energy suggests hidden dark sector interactions. Modified gravity challenges the framework itself. Chameleon and screening models try to explain why new forces might hide nearby but act far away. Each idea is motivated by something. Each idea struggles with something. None has yet walked calmly into the room, placed all the evidence on the table, and solved the case. There is a lesson here about names. Dark energy sounds like one thing, but in physics, it may refer to a family of possibilities. It may be vacuum energy. It may be a cosmological constant. It may be a scalar field. It may be an evolving substance. It may be a sign that gravity needs revision. It may be connected to quantum physics in a way we do not yet understand. The name dark energy is a placeholder for ignorance organized by evidence. It tells us there is an effect. It does not tell us the cause, and that is why measurements matter so much. Theories can multiply quickly. A clever physicist can produce new models the way a garden produces weeds after rain. Some may be beautiful, some may be useful, some may only be decorative. Observations are what decide which survive. Does dark energy change with time? Does it vary across space? Does it affect the growth of structure? Does gravity behave exactly as general relativity predicts on the larger scales? Do supernovae, galaxy clustering, gravitational lensing, and the cosmic microwave background tell the same story when combined? These questions are the filters through which suspects must pass. For now, the cosmological constant remains the quiet leading candidate. It is simple, and it works very well. But the very fact that it works so well while remaining theoretically puzzling keeps the other suspects alive. Physicists are not being indecisive, they are being careful. When a mystery touches the deepest parts of gravity, quantum theory, and cosmic history, it is wise not to close the case too early. The universe has already surprised us once by accelerating. It would be bold to assume it has no further surprises hidden in the fine print, so we leave the suspect list open. Quintessence sits there as the changing field. Phantom energy lurks with its dramatic future. Early dark energy waits near the beginning of cosmic history. Modified gravity questions the rules of the game. The cosmological constant remains steady, simple, and annoyingly hard to explain. Around them all, observations continue to tighten. Telescopes map more galaxies. Supernova samples grow. Ancient light is measured with increasing precision. The cosmic web becomes clearer, and through all of it, one particular tension has become especially important, because even before we know exactly what dark energy is, we must ask how fast the universe is expanding today, and why different methods do not always seem to agree. Before we can decide whether dark energy is a steady feature of empty space, a slowly changing field, a strange phantom influence, or a sign that gravity itself needs a quiet but serious talking to, we have to ask a deceptively simple question. How fast is the universe expanding right now? It sounds like the kind of question that ought to have a number attached to it, neat and reliable, perhaps written on a tidy card and placed in the drawer marked cosmic facts. The universe expands at this rate. There we are. Kettle on. Mystery reduced by 1. But cosmology is not always so obliging. The current expansion rate of the universe is known as the Hubble constant, named after Edwin Hubble, whose observations helped reveal that distant galaxies are moving away from us and that the universe itself is expanding. The word constant makes it sound reassuringly fixed, like the speed limit on a quiet road, or the number of biscuits one promises to eat before immediately revising the estimate. But the Hubble constant is not constant in the sense that the expansion rate has always been the same throughout cosmic history. It is the value of the expansion rate today. It tells us how quickly space is stretching now, in the present era of the universe, after nearly 14 billion years of cosmic change. Measuring that number should in principle tell us a great deal. It helps determine the age of the universe. It helps connect the early universe with the universe we see today. It helps test whether our model of dark energy is working. And because expansion is the stage on which the dark energy mystery performs its most suspicious little dance, getting the present rate right is not a minor bookkeeping matter. It is central. If the expansion rate is different depending on how you measure it, then something in our measurements, our assumptions, or our theory may be wrong, and that is exactly the trouble. There are 2 broad ways to measure the expansion rate, and they do not agree as well as they should. One method looks at the nearby universe, using a distance ladder built from stars and supernova. The other method looks at the early universe, using the ancient afterglow of the Big Bang, and our best model of how the universe evolved from then until now. The nearby method tends to give a higher value. The early universe method tends to give a lower value. The difference is not enormous in ordinary conversation, but in precision cosmology it is large enough to make everyone sit up slightly straighter. This disagreement is called the Hubble tension. The word tension is polite. Scientists are very good at polite words for deeply uncomfortable situations. Tension sounds calm, like a violin string being tuned. In reality, it means that 2 respected ways of measuring the universe are pulling against each other. It does not yet mean that our understanding of physics is broken. It does not automatically mean that dark energy is evolving, or that gravity is wrong, or that the universe has been hiding a secret note under the cosmic rug. But it does mean that something has to give. Either one set of measurements contains hidden errors, or the model used to connect early universe observations to today is missing something. Let us begin with the nearby method, because it is a little more like ordinary measuring, at least in spirit. Suppose you want to measure how fast nearby galaxies are receding. You need 2 things. You need their distances, and you need how quickly they are moving away from us due to cosmic expansion. The recession speed can be inferred from the stretching of their light. The distance is harder. Distance, as we have learned, is astronomy's most persistent headache. Space does not come labelled. Galaxies do not send invoices with addresses printed clearly at the top. Astronomers must build their way outward, one rung at a time. This is the cosmic distance ladder. The first rungs involve nearby stars whose distances can be measured directly, using the tiny shift in their apparent position as Earth moves around the Sun. Once nearby distances are known, astronomers use certain kinds of variable stars whose brightness changes in a predictable way. Cepheid variable stars are especially important. They brighten and dim with a rhythm that reveals their true brightness. If you know how bright a Cepheid truly is and how bright it appears, you can calculate how far away it is. These Cepheids can be found in nearby galaxies, and they help calibrate the brightness of Type 1a supernovae in those same galaxies. Then the supernovae take over for the deeper universe. As we discussed before, Type 1a supernova can be standardized and seen across enormous distances. So the ladder works like this. Nearby geometric measurements calibrate Cepheid stars. Cepheid stars calibrate supernova. Supernovae reach far enough to measure the expansion of the universe on large scales. It is elegant, but each rung must be carefully checked. A small error early in the ladder can affect the rungs above it. If your first step is tilted, the whole ladder becomes a little adventurous. Using this method, astronomers have often found a present expansion rate around the low 70s, in the usual units of kilometers per second per megaparsec. That unit is a mouthful, but it simply describes how much faster galaxies appear to recede for each large step of distance away from us. You do not need the arithmetic to understand the tension. The important point is that local measurements usually say the universe is expanding today faster than the value predicted from the early universe. Now let us turn to the other method, which begins not with nearby stars, but with the oldest light we can observe. The cosmic microwave background is the leftover glow from the early universe, released when the cosmos had cooled enough for light to travel freely. It comes to us from a time when the universe was only about 380,000 years old, which sounds ancient until you remember that the universe is now nearly 14 billion years old. In cosmic terms, the microwave background is baby light. Very well-travelled baby light, but baby light all the same. This ancient glow is not perfectly smooth. It contains tiny temperature variations, faint patterns that record the conditions of the young universe. Those patterns are rich with information. They tell us about the amount of ordinary matter, the amount of dark matter, the shape of space, the early expansion, and the seeds that later grew into galaxies and clusters. Missions such as Planck measured this glow with extraordinary precision. When scientists fit the standard cosmological model to the microwave background, they can infer what the expansion rate should be today. That inferred value is lower. It tends to come out around the high 60s in the same units. Not wildly different from the local value, but different enough that the uncertainty ranges do not comfortably overlap. The early universe says one thing, the nearby universe says another, and both are using impressive data, careful analysis, and decades of refinement. This is what makes the Hubble tension so interesting. If one measurement were obviously sloppy, the problem would be less exciting. If the local ladder depended on guesses scribbled on napkins, or if the microwave background were measured with something that looked suspiciously like a toaster, we could relax. But that is not the case. The local measurements have been improved with space telescopes, better calibrations and independent checks. The early universe measurements are among the great achievements of precision cosmology. The disagreement has persisted long enough that it cannot be waved away with a casual shrug. Of course, hidden errors are still possible. They always are. The history of science is full of effects that seemed revolutionary until someone found dust, calibration issues, selection bias, or a surprisingly mischievous piece of equipment. Local measurements could be affected by the calibration of Cepheids, the properties of supernovae, the influence of dust, the way stars crowd together in distant galaxies, or assumptions about the environments where the measurements are made. Early universe inferences could depend on assumptions built into the standard model, including the behavior of dark matter, radiation, neutrinos, and dark energy. The word inference matters. The microwave background does not directly measure the expansion rate today. It measures the early universe, and then a model carries that information forward. This is why the tension has two broad interpretations. One possibility is that there is an unrecognized measurement problem, something in the distance ladder, or in the early universe analysis, or in the comparison between them, has not been fully accounted for. This would be the less dramatic outcome, but not a boring one. Measurement problems can be subtle and deeply instructive. Finding one would improve cosmology and sharpen the tools used to study dark energy. It would be like discovering that the strange noise in the kitchen is not a ghost, but a loose pipe. Less thrilling, perhaps, but still useful, especially if you enjoy sleeping. The other possibility is new physics. That phrase should be handled gently. New physics does not mean everything we know is wrong. It means that the standard model of cosmology may be incomplete. Perhaps something happened in the early universe that changes the inferred expansion rate. Perhaps there was an extra form of energy before recombination, often called early dark energy. Perhaps dark matter has interactions we do not understand. Perhaps neutrinos behave in unexpected ways. Perhaps dark energy evolves over time. Perhaps gravity itself differs from general relativity on cosmic scales. Each idea tries to ease the tension by changing the bridge between the early universe and today. Early dark energy is one of the ideas that has received particular attention. In this picture, a small amount of dark energy or dark energy-like behavior appears in the early universe before fading away or becoming less important. This could change the size of the cosmic ruler imprinted in the microwave background and in the distribution of galaxies, allowing the inferred present expansion rate to rise closer to the locally measured value. It is a clever idea. But clever ideas must survive data from many directions. Early dark energy cannot be added freely. It affects the microwave background, galaxy formation, and other observables. Too much of it causes trouble. Too little does not solve the tension. The universe is not a soup into which one can simply add a pinch of mysterious energy and stir until the numbers taste right. Changing dark energy at later times is another possibility. If dark energy evolves, then the expansion history between the early universe and today may differ from the simplest model. That could affect the inferred Hubble constant. Recent galaxy surveys, especially those mapping the positions of millions of galaxies and quasars, are beginning to test this possibility with increasing precision. Some combinations of modern data have hinted that dark energy may not be perfectly constant, but hints are delicate things. They can grow into discoveries, or they can disappear when more data arrive, rather like that one sock you were sure had returned from the wash, but somehow did not. This is why the Hubble tension connects so deeply to dark energy. Dark energy controls the late expansion of the universe. The Hubble constant is the current expansion rate. If the current rate measured nearby does not match the rate predicted from early universe data, perhaps dark energy is not behaving exactly as assumed, or perhaps something else in the cosmic model is responsible. The tension does not point uniquely to dark energy, but it keeps dark energy very much in the conversation. There is another layer of difficulty. We do not live in a perfectly smooth universe. We live in a galaxy. Our galaxy belongs to a local group. The local group sits near other structures, voids, filaments, clusters, and flows of matter. Nearby galaxies are not only receding because of cosmic expansion, they also move under the gravitational influence of local structures. These extra motions must be accounted for. If you measure too locally, peculiar motions can distort the expansion signal. If you measure farther out, the signal becomes cleaner, but distances become harder. It is a balancing act. Cosmologists want measurements close enough to calibrate well, but far enough to represent the smooth expansion of the universe. This is one reason independent methods are so valuable. Geophids are not the only distance calibrators. Some teams use the tip of the red giant branch, a feature in the brightness of old stars that can also serve as a distance indicator. Others use masers, gravitational lensing time delays, surface brightness fluctuations, or other methods. Each has different strengths and weaknesses. If many independent techniques converge on the same value, confidence grows. If they scatter, the mystery deepens. Some methods produce values closer to the local supernova ladder. Some sit between the local and early universe results. The picture is not as simple as two numbers shouting at each other across the room, though that is the dramatic version. The Hubble Space Telescope played a central role in improving the local distance ladder. It could observe Cepheids in distant galaxies with less atmospheric blurring than ground-based telescopes. More recently, the James Webb Space Telescope has added another check, observing some of the same distance indicators with greater clarity in infrared light, where dust is less troublesome. The fact that Webb observations have supported the Hubble-based measurements has made the tension harder to dismiss as a simple instrument problem. That does not mean all systematic uncertainty is gone. In precision astronomy, uncertainty is like glitter. You may think you have cleaned it up, but then it appears again on a sleeve 3 days later. Still, the independent confirmation strengthens the case that the disagreement is real enough to take seriously. On the early universe side, the Planck mission gave an extraordinarily precise map of the cosmic microwave background. Its inferred expansion rate fits beautifully within the standard cosmological model, alongside many other measurements. The model is not a fragile little structure balanced on one observation. It explains a wide range of cosmic data. That is why changing it is difficult. Any proposed fix to the Hubble tension must not break the successful agreement elsewhere. A new ingredient that raises the inferred expansion rate may also change the microwave background in ways that are not observed, or alter galaxy clustering, or conflict with measurements of light elements from the early universe. Cosmology is interconnected. Pull one thread, and the whole cosmic jumper may begin to complain. So the Hubble tension remains unresolved because both sides have reasons to be trusted. Local measurements directly probe the recent universe and use distance indicators tested through multiple steps. Early universe measurements rely on a powerful, simple model that explains many observations with remarkable consistency. The disagreement sits between them, asking whether one side has a hidden flaw or whether the model connecting them is incomplete. This is not a small technical squabble. It touches the structure of modern cosmology. If the tension is due to new physics, it could reveal a new component of the universe, a new interaction, a change in dark energy, or a modification to our understanding of gravity. If it is due to measurement error, it will still teach us something important about how difficult it is to measure cosmic distances and expansion. Either outcome matters. The universe is either surprising us with new physics or with the subtlety of its measuring problems. Both are very on brand. There is also an emotional lesson in the Hubble tension, if science may be allowed a quiet emotional lesson now and then. It reminds us that precision does not always bring immediate clarity. Sometimes, the better we measure, the more visible the disagreement becomes. In older astronomy, uncertainties were large enough that different values could coexist comfortably. As the measurements improved, the cushions were removed. The numbers became sharper, and the gap between them became harder to ignore. That is progress, even when it feels inconvenient, especially when it feels inconvenient. For dark energy, the tension is a warning not to become too comfortable. The cosmological constant model works extremely well, but the universe may be telling us that the story has a hidden complication, or it may be telling us that measuring the present expansion rate is harder than we thought. Or, with its usual fondness for mischief, it may be doing both. Future observations will matter enormously. The Euclid mission, the Nancy Grace Roman Space Telescope, the Vera Rubin Observatory, and large galaxy surveys such as the Dark Energy Spectroscopic Instrument are designed to map the expansion history and growth of structure with far greater precision. They will not simply give one number. They will trace how expansion changes over time, how galaxies cluster, how gravity builds structure, and how dark energy leaves its fingerprints across billions of years. That is the path forward. Not one measurement, but many. Not one candle, but thousands. Not one ruler, but several kinds of cosmic ruler compared across time. Supernovae, Cephids, red giant stars, gravitational lenses, ancient microwave light, galaxy clustering, weak lensing, and the cosmic web all become part of the same investigation. If dark energy is constant, the evidence should increasingly settle around that story. If it evolves, the cracks should become clearer. If gravity changes, the growth of structure may reveal it. If the Hubble tension comes from a subtle systematic effect, better observation should expose where the ladder bends or where the early universe inference needs adjustment. For now, the Hubble tension remains one of the most important unsettled problems in cosmology. It is not proof that dark energy is changing. It is not proof that the standard model is wrong. But it is a persistent clue that something deserves attention. Like a quiet tapping at the window, it may turn out to be a branch in the wind, or it may be the universe asking to be let in. And that brings us back to the larger mystery. Dark energy was introduced to explain the accelerating expansion. The Hubble tension asks whether our measurements of that expansion, from the nearby universe and from the ancient universe, can truly be made to agree. The answer will shape what physicists believe dark energy is: a steady vacuum energy, a field that changes, a hidden early influence, a sign of modified gravity, or something no one has yet named because the right idea is still waiting, very patiently in the dark. The reason this matters is not only that it affects the number we attach to today's expansion, it affects the future. Once we know how the expansion is changing, and whether dark energy is constant or evolving, we can begin to ask what happens next. The universe may continue accelerating forever, carrying distant galaxies beyond view. It may drift into a cold, quiet future. It may behave more strangely if dark energy changes with time. The same mystery that complicates our measurements today also writes the long-term fate of everything, from galaxy clusters to the last faint light crossing space. The same mystery that complicates our measurements today also stretches far beyond us, into the deep future of the universe, where all ordinary human timescales become almost comically small. A century feels long to us. 1,000 years feels like ancient history. 1,000,000 years sounds enormous, the sort of duration that makes calendars give up and quietly leave the room. But cosmology thinks in billions, trillions, and far longer spans, where stars are born, burn, fade, and leave behind remnants, where galaxies change shape, where black holes slowly consume what wanders too near, and where the expansion of space keeps working in the background with patient, unsettling persistence. Dark energy matters because it does not merely describe what the universe is doing now, it helps decide what the universe may become. If it stays constant, the future is one kind of story. If it weakens, another story opens. If it grows stronger, a far more dramatic possibility appears. And if it is not energy at all, but a sign that gravity behaves differently across the larger scales, then the future may depend on a law of nature we have not yet written properly. That is why physicists keep trying to understand it. Dark energy is not just a mystery ingredient in a cosmic recipe. It is one of the main clues to the fate of everything. Let us begin with the simplest case, the one most closely connected to Einstein's old cosmological constant. In this picture, dark energy remains constant. It does not dilute as the universe expands. It does not grow stronger or weaker with time. It is simply there, associated with space itself, smooth and steady, like an extremely quiet guest who somehow ends up controlling the seating plan. Matter becomes more spread out as the universe grows. Radiation weakens as its light is stretched. But dark energy, if it is truly constant, keeps the same density in every region of space. This means that as time passes, dark energy becomes increasingly dominant. In the early universe, matter and radiation were much more important. Gravity pulled matter into clumps, gas collected, stars formed, galaxies assembled. Clusters and filaments grew into the cosmic web. Dark energy may have been present, but it was not running the show. Then, as space expanded, matter thinned out. Its average density fell. Eventually, the constant dark energy became the largest influence on the overall expansion. That is the era we now live in, the era when expansion is accelerating. If that continues forever, distant galaxies beyond our local gravitational neighborhood will drift farther and farther away. This does not mean that every object expands away from every other object. It is important to be careful here, because the phrase expanding universe can lead to odd pictures. The Earth is not expanding. Your house is not expanding. The distance between your teacup and your biscuit is not increasing because of dark energy, unless someone is moving the plate, in which case the cause is more likely human than cosmological. Bound systems remain bound. Atoms are held together by electromagnetic forces. Planets are held by gravity to stars. Stars are held in galaxies. Galaxies inside gravitationally bound groups can remain together. Our own Milky Way and the Andromeda Galaxy are expected to merge far in the future, because they are gravitationally bound to one another. Dark energy does not stop that local future. It does not pry apart every nearby system in the simple constant model. Instead, it dominates across enormous distances between galaxy clusters that are not bound to each other. The cosmic expansion stretches those separations more and more quickly, while local structures hold together like islands in a growing sea. Over enough time, this changes what any future astronomer could see. Galaxies that are now distant will recede so far that their light can no longer reach us. More precisely, the expansion of space will carry them beyond a cosmic horizon. Light they emit after a certain point will never arrive, no matter how long one waits. It is not that the light becomes lazy or loses interest. It is that the space between grows too quickly for the light to close the gap. Future observers in our local merged galaxy may look out and see far fewer signs of the wider universe. The great cosmic web will fade from view. The evidence for expansion, other galaxies, and even the hot early universe may become harder or impossible to detect. That is a strange thought. We happen to live at a time when the universe is old enough for galaxies, stars, planets, and life to exist, but young enough that the wider cosmos is still visible. We can see distant galaxies. We can measure the cosmic microwave background. We can infer the Big Bang and the expansion history. We can discover dark energy. A much later civilization, if one arises in the far future around long-lived stars, may not have access to the same evidence. Their night sky could be much emptier. They might think their galaxy is all there is, not because they lack curiosity, but because the universe has hidden the clues. There is something almost unfair about that. The cosmos has a limited viewing window, and we appear to be sitting inside it with our telescopes, notebooks, and occasionally underwhelming weather forecasts. The future universe may be quieter, darker, and more isolated. Not suddenly, not violently, but gradually over spans so long that even mountains would seem like passing thoughts. Distant galaxies will fade beyond reach. Star formation will slow as gas is used up or locked away. The bright, busy universe of new stars will become a universe of aging stars, remnants, and darkness. This long future is often connected with the idea of heat death. The phrase sounds dramatic, but it does not mean the universe becomes hot. In fact, it becomes colder and more spread out. Heat death means that usable energy becomes less and less available. Differences in temperature and energy, the differences that allow work to happen, gradually disappear or become inaccessible. Stars burn through their fuel. New stars form less often. Matter ends up in stable remnants, black holes, cold planets, and faint drifting objects. The universe moves toward a state where there may be plenty of energy in a technical sense, but very little that can be used to do anything interesting. If dark energy remains constant, this cold and accelerating future is the most commonly discussed outcome. Space continues expanding. Bound islands remain, but the gaps between them grow. The cosmic horizon limits what can be seen or reached. Over extraordinary times, stars fade. Black holes dominate some regions, then eventually, according to our current understanding, they may very slowly radiate away. This happens on timescales so enormous that ordinary language begins to feel a little embarrassed. The numbers are not just large. They are the kind of large that make the age of the universe so far look like the first sip of tea before a very long evening. But that is only one possible future, because it depends on dark energy being constant. If dark energy weakens over time, the acceleration could slow. The universe might still expand forever, but less aggressively. Distant galaxies would still move away, but the future would be less empty than in the constant dark energy case. Structures would remain visible for longer. The cosmic horizon might behave differently. The long-term fate could become less certain. A weakening dark energy would suggest that the force, field, or mechanism behind cosmic acceleration is dynamic. It would not be a fixed property of space. It would be part of the universe's evolving history. Some models of quintessence behave this way. A field changes slowly, and its effect on expansion changes with it. Depending on how it evolves, dark energy might fade enough that matter again becomes relatively more important, though by then matter would be extremely diluted. The universe might coast, expanding but no longer accelerating as strongly. In some more unusual scenarios, dark energy could even change sign or become attractive rather than repulsive on cosmic scales. That could open the possibility of a future collapse, sometimes called a big crunch, where expansion eventually halts and reverses. A big crunch is not favoured by the simplest current picture, but it remains useful as a reminder that the fate of the universe depends on the physics we have not fully understood. If dark energy is not constant, the future is not locked into one script. A field can change. A hidden interaction can evolve. Gravity itself may behave differently as the universe ages. The far future is not measured directly. It is inferred from laws and observations. If the laws are incomplete, then our forecast may be incomplete too. Then there is the more dramatic possibility, phantom energy. If dark energy grows stronger as the universe expands, the future becomes much stranger. In ordinary constant dark energy, bound systems are safe. Galaxies, solar systems, planets, and atoms remain held together by local forces. Phantom energy changes that. If its density increases without limit, its effect could eventually become strong enough to overcome all bound structures. First, galaxy clusters would be pulled apart. Later, galaxies, then solar systems, then planets. In the most extreme version, even atoms would be torn apart as the expansion becomes overwhelmingly powerful. This is the Big Rip. The Big Rip is a vivid idea, which is why it appears so often in popular discussions. It has the dramatic neatness of a cosmic disaster film, although one with a schedule too long for practical ticket sales. But it is important to be clear. It is not the leading expectation. It requires a particular kind of dark energy behaviour that is speculative and theoretically difficult. Phantom energy often causes problems in the underlying physics, and current observations do not require it. The Big Rip is a possible future in some models, not a prediction we should write into our diaries under things to worry about after lunch. Still, it teaches something important. Small differences in dark energy behaviour can have enormous consequences. If the energy stays constant, the universe drifts toward isolation and cold darkness. If it weakens, the expansion history may soften. If it strengthens, the future can become violent. If it changes in more complex ways, the possibilities multiply. The far future is not decided simply by the fact that expansion is accelerating now. It is decided by what dark energy is. There is also a possible future known sometimes as the Big Freeze, which is closely related to heat death in an ever-expanding universe. In this picture, the universe expands forever and cools. Galaxies outside bound groups disappear beyond the horizon. Star formation eventually ends. The remaining stars fade. White dwarfs cool. Neutron stars sit in darkness. Black holes become the last great stores of mass and energy. Then over unthinkable times they too may evaporate. The universe becomes thin, cold, and quiet. Not destroyed in a sudden event, but emptied of activity. This is not a cheerful future in ordinary human terms, but cosmology is not here to provide cheerful endings. It is here to follow the evidence. And there is a kind of calm in understanding that these futures lie so far beyond us that they do not intrude on daily life. Dark energy is not a storm on the horizon. It is a slow change in the horizon itself. Its timescales are vast. The sun will evolve through its own future long before the deepest dark energy outcomes matter locally. Earth has more immediate astronomical concerns than the ultimate fate of the cosmic web, which is comforting in one way and not comforting at all in another. Another possibility, stranger and more speculative, is vacuum decay. This is not exactly a dark energy future in the ordinary sense, but it connects to the nature of empty space. If what we call the vacuum is not the lowest possible energy state, then the universe might be living in a false vacuum, a stable enough condition that could, in principle, transition to a lower energy state. Such a transition would spread at nearly the speed of light, changing the laws or properties of physics as it went. This sounds alarming, and it is often presented in alarming tones, but it is highly speculative, and there is no evidence that such an event is imminent or likely on any meaningful timescale. It belongs more to the deep questions of quantum fields and cosmology than to practical worry. The reason to mention it gently is that it shows how deeply the future depends on the vacuum. If dark energy is vacuum energy, then understanding the vacuum is not optional. It affects expansion now, and it may connect to the stability and ultimate behavior of reality. Empty space, once again, refuses to be empty in a simple way. It may be the quiet engine of acceleration, the source of a theoretical embarrassment, and a clue to whether the universe's present state is truly permanent. There are also cyclic possibilities, though dark energy makes them difficult. Some theories imagine that the universe may go through repeated phases of expansion and contraction, or that our expanding universe emerged from a previous state. A strong, positive dark energy pushes against future collapse, making simple cycles less likely in the standard picture. But if dark energy changes, decays, or becomes negative in the far future, more exotic scenarios become possible. These ideas are speculative and not established, but they remain part of the larger effort to understand whether cosmic history has a beginning, an ending, or something more subtle than either. What all these futures have in common is uncertainty. Not total uncertainty, because we do know a great deal. We know the universe is expanding. We know the expansion is accelerating in the present era. We know dark energy, or whatever causes the acceleration, is smooth enough and influential enough to dominate the large-scale expansion. We know the simplest model fits many observations, but we do not know whether dark energy is truly constant. We do not know whether it evolves. We do not know whether it is vacuum energy, a field, a modification of gravity, or a sign of something deeper. The far future is a mirror held up to that ignorance. It shows us how much depends on the answer. This is why missions and surveys designed to measure dark energy are, in a sense, also measuring destiny. When Euclid maps billions of galaxies across cosmic time, when Roman studies supernovae and weak gravitational lensing, when Rubin repeatedly scans the sky, when ground-based spectroscopic surveys chart the cosmic web, they are not only asking what happened in the past, They're asking what the expansion is doing well enough to infer what it may do next. Every improvement in the history of expansion sharpens the possible futures. Every better measurement of structure growth tests whether gravity and dark energy behave as expected. One of the most important things to learn is whether dark energy's effect has changed. A constant dark energy leaves one pattern in the relationship between distance, redshift, galaxy clustering, and structure growth. A changing dark energy leaves another. Modified gravity may leave a mismatch between expansion and the way matter clumps. Phantom energy would point toward a more dangerous far future, while weakening dark energy could soften acceleration or change the fate entirely. These differences are subtle in present data, but not invisible. The universe has written its history into light and structure. The challenge is learning to read the handwriting. There is something oddly intimate about this despite the scale. The fate of the universe sounds impossibly remote, and it is. Yet the question touches the same reality that surrounds us now. The dark energy shaping the space between galaxy clusters is part of the universe in which your room, your breathing, your thoughts, and your small evening rituals exist. The far future is not separate from the present. It is the present allowed to continue under the laws of physics for a very long time. A cup cools because of thermodynamics. A star burns because of nuclear fusion. A galaxy recedes because space expands. The future grows out of the same rules that make the current moment possible, and perhaps that is why dark energy feels so unsettling. It is not only unknown, it is consequential. Some mysteries can remain local and charming. A missing sock, a strange noise in the attic. The exact reason one always opens the fridge twice when hungry, as though new food may have appeared through optimism alone. Dark energy is different. It decides whether the universe becomes increasingly isolated, whether acceleration changes, whether the horizon closes around each gravitational island, whether the cosmic story stretches into cold emptiness or bends towards some stranger ending. For now, the safest broad expectation, if the standard model remains correct, is that the universe continues accelerating and drifts toward a cold, dark, increasingly empty future. Distant galaxies disappear from view, local bound structures remain, stars gradually exhaust their fuel, the cosmos becomes quieter. This is not a sudden ending, it is a long fading, a slow dimming of possibility across timescales almost beyond comprehension. The universe does not slam the door. It leaves the room one light at a time. But physics has learned not to mistake the simplest forecast for final truth. Dark energy may yet surprise us. The recent hints from galaxy surveys, the persistent Hubble tension, the theoretical discomfort of vacuum energy, and the open possibilities of evolving fields or modified gravity all remind us that the future is tied to a mystery still unresolved. We can describe possible endings, but the correct ending depends on the nature of the darkness driving acceleration. So the far future of everything is not written in one clear sentence. It is written in conditional language. If dark energy is constant, then one path. If it grows, another. If it fades, another. If gravity changes, another. If the vacuum has deeper structure, perhaps something else entirely. The universe is expanding today, and that expansion is accelerating, but the meaning of that fact remains unfinished. To know the future, we must know the cause, and to know the cause, we must return once more to the central question that has followed us from distant supernovae to empty space, from Einstein's old term to the tension in modern measurements. Why, after all this observing, calculating, mapping and wondering, does the universe still keep dark energy hidden from us? After all of this, after the supernovae, the expanding space, Einstein's old idea, the vacuum energy puzzle, the possible fields, the phantom futures, and the stubborn disagreement over how fast the universe is expanding today, we return to the quiet question at the centre of it all. Why do physicists still not know what dark energy is? It is tempting to imagine that a mystery this large must be hiding, because we have not looked hard enough. Perhaps if we built one more telescope, made one more map, measured one more distant galaxy, the answer would step out politely from behind a nebula and say, "Apologies for the delay, I was vacuum energy all along." But science rarely works with such theatrical neatness. The universe does not hide its secrets in locked boxes with tidy labels. It hides them in patterns, in faint differences, in light stretched across billions of years, in effects so smooth and subtle that they only appear when you stop looking at individual stars and begin looking at the behaviour of the cosmos as a whole. Dark energy is especially difficult because it is not something we can isolate. We cannot scoop up a spoonful of it from the space between galaxies. We cannot hold it in a detector. We cannot turn it on and off, compare a universe with it to a universe without it, and then write a helpful laboratory report before lunch. It reveals itself through the expansion of space, through the way distances grow, through the relationship between ancient light and modern galaxies, through the large-scale history of cosmic structure. It is known by its consequences, not by its face. That makes it different from many discoveries in physics. Electrons could be studied in experiments. Atoms could be probed. Light could be split, bent, reflected, absorbed, and persuaded to do all sorts of useful things, some of them eventually leading to devices that allow people to watch cat videos at unreasonable hours. Even gravity, although invisible, can be tested through falling objects, orbiting planets, bending light, and colliding black holes. Dark energy, by contrast, is almost absurdly gentle on ordinary scales. It does not tug at your sleeve, it does not rattle the windows, it does not make your toast hover ominously above the plate. Its influence is cosmic. Its fingerprints are written across distances so vast that human intuition arrives with a suitcase and immediately feels underdressed. The first reason the secret remains hidden is scale. Dark energy becomes important across the largest spans of space and time. The acceleration it causes is not something you notice in a room, a city, a solar system, or even inside a galaxy. Local systems are held together by stronger effects. Atoms by electromagnetic forces, planets and stars by gravity, galaxies by gravity. Even galaxy groups can remain bound. Dark energy shows itself only when we compare enormous regions of the universe that are not gravitationally tied together. It is like trying to understand a tide so broad that no single wave looks unusual from where you're standing. The second reason is that the evidence is indirect. Physicists did not discover dark energy by detecting a new particle buzzing through a chamber. They inferred it because the universe's expansion was not behaving as matter and gravity alone predicted. Distant supernovae were dimmer than expected. The cosmic microwave background fit a universe with a large smooth component. Galaxy patterns and cosmic rulers supported the broader picture. These are powerful clues. They are not weak, they are not casual guesses, but they tell us what dark energy does more clearly than they tell us what it is. That distinction matters. A description is not the same as an explanation. We can describe dark energy as something that drives the accelerated expansion of the universe. We can describe the simplest version as a constant energy of space. We can say how it behaves in our models, but when we ask why empty space should have that energy, why the value should be so tiny, why it should be present at all, and whether it truly remains constant forever, the answers become much less secure. The map is useful, the terrain is still strange. The terrain. This happens often in science. Long before people understood what heat really was, they could measure temperature and build steam engines. Long before anyone understood the deep quantum nature of light, people used lenses, mirrors, and prisms. A phenomenon can be real and useful before its deepest explanation is known. Dark energy may be in that stage now. We can include it in cosmological models. We can measure its effects. We can test whether it behaves like a constant or a changing field. But the deeper identity remains out of reach. The third reason is that our best theories do not yet meet cleanly where dark energy lives. General relativity describes gravity and the large-scale structure of space and time with extraordinary success. Quantum field theory describes particles and fields with extraordinary success. But dark energy seems to sit at the awkward dinner table between them. If it is vacuum energy, it belongs to quantum fields. But if it shapes the expansion of the universe, it belongs to gravity and cosmology. When physicists try to connect those descriptions, the vacuum energy problem appears, with its enormous mismatch between what theory seems to suggest and what the universe appears to allow. This is not just a technical inconvenience. It is a sign that something deep is missing. Perhaps we do not understand how vacuum energy gravitates. Perhaps asymmetry cancels most of it. Perhaps the correct theory of quantum gravity changes the story. Perhaps dark energy is not vacuum energy at all. Each possibility leads into difficult territory. The reason the secret remains is not that scientists have no ideas. It is that they have too many possible ideas and not yet enough decisive evidence to choose between them. The fourth reason is that the simplest answer is annoyingly successful. A constant energy of space fits many observations remarkably well. It is simple. It is stable. It does not require elaborate new behaviour. If the universe were a puzzle, this piece would slide into place with suspicious ease. But once it is in place, it raises uncomfortable questions about why the piece has that shape in the first place. This creates a peculiar scientific tension. Observationally, the simple model works. Theoretically, it feels incomplete. Physicists are left in the position of using an explanation that describes the data beautifully, while suspecting that the deeper explanation is still hidden underneath. That can be frustrating, but is also a sign of maturity in science. A less careful field might declare victory too early. Cosmology does not have that luxury. The data are too precise, the implications too large, and the theoretical problems too serious. So physicists continue to test the simple model, not because it is weak, but because it is important. If dark energy is truly constant, that is a profound fact about empty space. If it is not, then finding the deviation may be the key to new physics. The fifth reason is that dark energy might be changing only slightly, and slight changes are difficult to see. Suppose dark energy is not exactly constant, but evolves slowly over billions of years. That would not be easy to detect. The signal would be spread across cosmic time and mixed with other effects. Supernova brightness, galaxy clustering, gravitational lensing, the cosmic microwave background, local distance measurements, and the growth of structure would all need to be combined carefully. Each carries uncertainties. Each depends on calibrations and assumptions. A tiny change in dark energy can hide among the ordinary difficulties of measuring a very large universe from one small planet with weather. This is why modern surveys are so ambitious. They are not simply taking prettier pictures of galaxies, although some of the pictures are indeed very pretty and deserve a moment of quiet appreciation. They are mapping the universe across time. They are measuring how galaxies cluster, how light bends around mass, how cosmic distances compare at different eras, and how structures grew under the competing influences of gravity and expansion. A changing dark energy should leave a different pattern than a constant one, but the pattern is faint. The measurement has to be enormous. The sixth reason is that the universe gives us only one universe to study. This is easy to overlook. In many sciences, you can repeat experiments, you can change conditions, you can run trials, you can compare one sample with another. Cosmology is different. There is one observable universe. We cannot restart it with dark energy set a little higher, then again with it set a little lower, and see which version makes better galaxies. We cannot build a spare cosmos in a laboratory, though one suspects the safety paperwork would be memorable. We observe the universe we have from the location and time we occupy, and infer as much as possible. That makes cosmic variance and limited perspective important. We see only the observable region, not the whole of whatever may exist beyond it. We measure light that reaches us, not light forever beyond our horizon. We reconstruct history from signals that survive the journey. The universe is generous, but not unlimited. It gives us clues, not control. The seventh reason is that dark energy may be entangled with other unknowns. It is not the only mystery in cosmology. Dark matter remains unidentified. The Hubble tension remains unresolved. The early universe still contains questions about inflation, initial conditions, and the origin of cosmic structure. Neutrinos have properties that still matter for cosmology. Black holes and quantum gravity raise deep puzzles. When a measurement does not match the simplest model, it can be hard to know which unknown is responsible. Is the clue pointing to evolving dark energy, hidden systematics in supernovae, unusual dark matter behavior, early universe physics, modified gravity, or something else entirely? The universe does not colour-code its mysteries, which is inconsiderate. This is why multiple lines of evidence are essential. Supernovae measure distances. Galaxy clustering provides cosmic rulers. Weak lensing maps the growth of structure and the distribution of mass. The cosmic microwave background gives the early universe. Local distance ladders measure the present expansion rate. Each method has different weaknesses. If they all point in the same direction, confidence grows. If they disagree, the disagreement itself becomes a clue. But clues can be ambiguous. The Hubble tension might point to new physics, or hidden measurement problems, or a mixture of both. Recent hints of evolving dark energy might grow stronger, or soften with better data. Cosmology must be patient enough to let the universe finish its sentence. The eighth reason is philosophical in a very practical way. We're asking whether something is fundamental or emergent. If dark energy is the cosmological constant, perhaps it is a basic property of space. If it is quintessence, perhaps it is a field. If it is modified gravity, perhaps it is not energy at all but a sign that our equations need revision. If it is connected to quantum vacuum structure, perhaps it emerges from deeper physics we do not yet possess. These are different kinds of answers. They do not merely name different substances, they describe different ideas about what space, time, gravity and energy are. That is why dark energy feels deeper than a missing ingredient. It may be telling us something about the nature of empty space itself. An empty space is not a minor character. It is the arena in which everything else happens. If space has energy, if that energy determines cosmic fate, if its value depends on quantum fields or deeper laws, then dark energy is not just an astronomical puzzle. It is a question about the foundations of reality. No wonder it has been difficult. Yet the difficulty should not make the mystery feel hopeless. In fact, the situation is better than it may sound. Physicists know much more than they did before the supernova discovery. They know the expansion is accelerating. They know the simple constant model works very well. They know the approximate size of the effect. They know what kinds of alternatives are allowed and which are tightly constrained. They have built surveys specifically designed to test whether dark energy evolves. They have better instruments, more data, and sharper methods than ever before. The secret remains, but the room around it is getting smaller. There is a lovely image in that. Imagine a dark room with something quiet inside it. At first you know only that something is there because the furniture is not where it should be. Then you begin to map the room by touch. A table here, a chair there, a window, a wall. Each measurement does not reveal the hidden object directly, but it limits where the object can be. Eventually the shape of the absence becomes informative. Dark energy is like that. We do not see it directly, but its effects constrain it. The unknown has edges. And perhaps that is what makes the mystery so compelling. It is not ignorance in the vague sense. It is precise ignorance. Scientists do not simply shrug and say dark energy is mysterious. They can say how it behaves in the simplest model. They can say what observations support it. They can say what alternatives would change. They can say what future measurements must test. They can say where the confusion lies. That is a powerful kind of not knowing. It is not darkness without direction. It is darkness with instruments pointed into it. Still, the universe keeps the secret because the answer may require a theory we have not yet completed. General relativity and quantum physics are both magnificent, but they are not unified. The cosmological constant problem may be a symptom of that unfinished work. Dark energy may be a clue from the borderland where our theories overlap imperfectly. If so, solving it may require more than better measurements. It may require a new conceptual step, a way of understanding vacuum, gravity, and cosmic expansion together. Not a patch, not a clever adjustment, a deeper picture. Scientific history gives some comfort here. The motion of planets once looked puzzling until gravity was understood in a new way. The spectrum of light from atoms seemed mysterious until quantum mechanics arrived. The orbit of Mercury contained a tiny anomaly that became a clue to general relativity. Small disagreements, stubborn numbers, and unexplained patterns have often led to major advances. Dark energy may be one of those clues, a cosmic whisper that something about our deepest framework is unfinished. But we should also allow for the possibility that the answer is simple and strange. Perhaps dark energy really is just the cosmological constant. Perhaps empty space has a small constant energy, and the deeper reason for its value is hidden in principles we may one day understand, or perhaps in a selection effect across a larger cosmic landscape. That answer may not feel emotionally satisfying, but nature is not required to provide satisfying answers. It provides true ones, and even those only after we work very hard. So where does that leave us tonight? With a universe that is expanding faster over time, with a name for the unknown cause, with a simple model that works well and deeper theories that struggle to explain it, with hints that may or may not become cracks, with telescopes mapping billions of galaxies, supernovae still serving as distant candles, and ancient light still carrying messages from the early universe, with physicists asking whether the darkness is vacuum energy, a field, modified gravity, or something stranger, and with us here thinking about it softly. There is something rather beautiful about being alive during a time when this question can be asked properly. For most of human history, the universe looked like a ceiling of stars. Then it became a galaxy, then many galaxies, then an expanding cosmos, then an accelerating one. Each step made reality larger and less familiar. Each step also made it more understandable, not because the mystery vanished, but because our questions improved. Dark energy may remain unknown, but it's not beyond science. It is being measured, tested, cornered slowly by evidence. The fact that physicists do not yet know what it is does not mean they are lost. It means they have reached one of the places where knowledge is still being made. A frontier is not a wall. It is where the map becomes active. And perhaps, as we come to the end of this quiet journey, that is the gentlest way to hold the mystery. The universe is not obligated to reveal itself all at once. It has taken billions of years for light from distant supernovae to reach us. It has taken generations of thought to understand expansion, gravity, quantum fields, and cosmic history well enough to see the question clearly. The secret is not kept from us out of cruelty. It is hidden because nature is deep, and we are still learning how to listen. So, wherever you are tonight, whether the sky above you is clear or clouded, whether the stars are visible or lost behind city lights, the same dark energy mystery surrounds you on the larger scales. Not pressing, not rushing, not disturbing the little room you're in, but shaping the great distances between galaxies, guiding the far future of cosmic expansion, and reminding us that even in an age of powerful telescopes and precise measurements, the universe can still keep a little silence for itself. And if this journey through the dark has brought you a little calm, or given your thoughts somewhere wide and quiet to wander, I would be ever so grateful if you liked the video, subscribed, and shared this sleepy corner of science with another curious traveller. The cosmos is vast, the questions are patient, and tonight there is no need to solve all of them. Let the mystery remain where it is for now, out among the galaxies, in the stretching of space, in the soft, unfinished edge of human understanding. Sleep well, fellow traveller. The universe is still expanding, still whispering, still keeping some of its secrets, and here, for this moment, beneath all that darkness, you are simply here,